Afternoon, everybody. Welcome to our Mars 2020 Perseverance Landing virtual event. My name is Chris, and I am your host for today's program. I work at the North Carolina Museum of Natural Sciences, and our team at the museum is bringing you this 5-hour event dedicated to helping us learn more about Mars, the red planet, and today's so special guest, the Perseverance rover. That's right, everybody. Today, NASA will be hopefully landing a brand new machine on the surface of Mars to help us learn more about the red planet. Throughout the day today, we have special guests who will be giving presentations, sharing insights and their knowledge about Mars and the Perseverance mission. We'll be hearing from several local NASA-JPL solar system ambassadors and astrophysicists. We have crafts and activities set up for you. So check out naturalsciences.org. Look for the Perseverance landing event image, click on that, and then take a look at the schedule of events today. Because if you don't want to sit for all 5 hours today, as we gear up to the landing event itself, which we will stream live and carry right here on the museum's YouTube channel, you can sort of pick and choose the things you want to do, but I hope you'll stay with us for as long as you can. For today, it's not just me who will be hosting the show. Let me bring on my very special co-host today. Alan Rich is a NASA-JPL solar system ambassador, and I'll say it, expert. Alan, welcome to the show.
Thanks, Chris. I got his name wrong during practice. So the museum's doing a great job with this. Really appreciate what all they've set up for here. Today is the day. Today it's all about what we call EDL, and that's an acronym for entry, descent, and landing, which is what the robot's doing. The Perseverance robot is headed towards Mars, is arriving there as we speak at over 12,000 miles an hour. And entry into the atmosphere, descent, going towards the ground, landing, the 7 minutes of terror. And that's what today is about. NASA's biggest, smartest, best ever, and also the cleanest robot, well, that's a long story, robot ever built is entering Mars and should land at about right around 4 o'clock this afternoon. And behind me here, I've got, we're watching the radio signals, the communication. This is the NASA's Deep Space Network. We have radio dishes all over in 3 different places around the globe. We're not here in North Carolina, we're not pointed at Mars right now, but Madrid is. The station that we like in the United States is Goldstone, which is in Mojave Desert, about halfway between Los Angeles and Las Vegas. And these are the dishes there. They're talking to different spacecraft. You can see the little squiggly lines. That means there's signals coming in and out. But Madrid is what we're interested in right now in Spain, because Spain is facing Mars. And there's 2 radio dishes here that are talking to Perseverance, the Mars 2020 robot right now. And there's little squiggly lines. That means the signal is coming back and forth, and we're talking to Perseverance. And, you know, Perseverance is seeing, you know, Mars coming up at 12,000 miles an hour. So Percy's probably saying, no, I don't want to do this. This is, I miss Pasadena, the Rose Bowl parade, everything. Let me go home, you know, clubbing in Los Angeles, doing the robot. You know, let me come home. This is not, no. And mission control is probably, when you see the outgoing signal saying, oh, just shut up, you're landing on Mars today. Landing on Mars about 4 o'clock. Another thing you might notice, when we're giving live feed to mission control at JPL, our special dry roasted peanuts. These are NASA brand dry roasted peanuts. If you want the peanuts, the only brand that has luck as an ingredient, I'll tell you the story behind these. These are eaten, but not really NASA peanuts. NASA just makes robots and spacecraft. NASA does not make peanuts. But if they did, that's what's eaten. During JPL, NASA had about 20 years ago a bad streak of bad luck, launching things, landing things, and somebody brought some dry roasted peanuts to mission control, and we had a great mission. And they thought, let's make this a tradition. So now if you go to visit Mission Control at JPL in Pasadena, there's jars of peanuts everywhere. Whenever there's a tense moment and you really need things to go right and you're nervous and you've got anxiety, people start eating dry roasted peanuts. And I've got some here. I'm going to be eating about a jar of these today, because what happens, as I told you before, called the 7 minutes of terror. It's we're going to go into that quite a bit and have some people talk about that. Coming in hot, 17,000 miles per hour, opening a supersonic parachute that you can't even test on Earth. You have to test it on Mars. And then the crazy, creepy sky crane maneuver, where this artificially intelligent rocket-powered robot that actually has the Perseverance robot underneath flies around and, without the help of any humans, looks for a good place to land Perseverance, the main robot, drops it on bungee cords, drops it off on the planet, then flies away. That is terrifying, and it's crazy, but that's what we're going to do about 4 o'clock this afternoon. So stay with us with these presentations. As Chris said, we've got, between now and then, we've got all kinds of stuff, fun for the whole family. We've got a robot building. Let's see, that's about at 1 o'clock. We've got a make your own robot exercise at home from Sarah Taylor, NASA-JPL Solar System Ambassador. We've got something else for you at 1:30. Doug Lively and I will be showing you a thing called Eyes on the Solar System, where you can connect to computers at NASA in JPL in Pasadena to go out and explore what's out there in space, wherever you want to go, including the car that Elon Musk put up there. Wherever you want to go, whatever you want to look at, we've got that you can do on your own computer or even your smartphone from home. And I'm going to show you how to do that. Super, super cool. And we have other programs, technical programs we've got coming up in at 12:30. Astrophysicist Dr. Rachel Smith is going to talk about the search for life on Mars. And coming up here in just a few minutes, 3 of the solar system ambassadors are going to be telling you about the science instruments on the robot Perseverance and how it's going to look for evidence of past life and habitability on Mars. Then from 2 to 3:30 or so, we've got presentations on the robot itself, show you all about it, all the different parts, how it works. We've got a presentation on the history of Mars exploration. Everything that's Mars is not a really nice place to try to explore. Like almost half of the missions that different countries around the world have attempted to put on Mars have failed. Mars is not easy at all. So we're going to have a program to show you some of the successes and some of the failures. Then at about 3 o'clock, we're going to have a presentation on this crazy EDL, entry, descent, and landing, right before it happens. We're going to tell you how that works. Then we're going to show you a really cool animation that's going to parallel in real time, and I'll tell you why. It's going to parallel in real time what's going on as we watch the presentation. The reason for that is when the robot is doing EDL, entry, descent, and landing at Mars, you're about 11 light minutes away for the signal to get back. So when the robot lands on Mars, it's hopefully going to send I'm here, I'm safe, I'm on the ground signal, but it's going to take that signal. Signal travels at the speed of light. It's going to take that signal 11 minutes to get back to mission control by way of Madrid in Spain. It's going to take 11 minutes to get back Madrid to Pasadena before everybody screams and says, hey, it's on the ground and it's safe. So we're going to show you what's happening real time when it's really happening, but we don't know if it's really happening like that until 11 minutes later when the robot contacts us and says, I'm okay. So that's coming up at this entry, descent, landing starts at about 3:48 p.m. this afternoon. We'll show that. And then we switch live to JPL Mission Control in Pasadena, where we nervously eat peanuts and wait for the robot to call us and tell us that it's there. So hang on for all this stuff. We got 5 hours of great stuff for you today. And it's not nice outside. probably. So watch us instead. And afterwards, starting at about 4:15, hang on for that, because we're all kind of tight schedule here until the landing. At about 4:15 until 5, we're opening it up to questions and answers from you guys. So any questions and anything you want to talk about that you think of during the day, hold that for about 4:15, and then we'll be live with all the solar system ambassadors to talk to you and answer your questions until about 5 o'clock. That was kind of an intro of everything we got going. The first presentation I told you coming up in just a couple of minutes is the science instrumentation on Perseverance robot, how it's going to study Mars, looking for signs of life or signs of previous life or signs of habitability. Adam Hauser, Tony Rice, and Matthew Funke from the Solar System Ambassadors from North Carolina are going to be doing that for you here in just a few minutes. Chris, what do you got? You got anything else?
Well, I've got one question for you, and then I'm going to turn it over to Adam, Tony, and Matthew for their presentation. When did the Perseverance launch happen? How long has Perseverance been en route to Mars?
That's a good question. Percy has been on route to Mars about 8 months, and that's everything everybody sends to Mars takes about 8 months. And there's a reason for that. There's, give or take a few weeks. There's a reason for that. We only launch every couple of years, not just us, but everybody, because you got to wait till the Earth and the Mars are in a good position relative to each other, fairly close, and then when you launch, we go into a specific kind of orbit called the Hohmann transfer orbit, where you exceed escape velocity from the Earth. You don't exceed escape velocity from the sun. You don't go that fast. So you put yourself in orbit, in its orbit around the sun on your way to Mars. And you time that so that the intersection of your spacecraft orbit around the sun intersects with Mars orbit around the sun. When Mars is there, hopefully, when it intersects. And that's how we do it. And that just takes about 8 months, no matter what size rocket you have. A bigger rocket won't really get you there much quicker. So that's the way we always do things to Mars, every 2 years and then 8 months to travel.
Thanks, Alan. So everybody, it's been 8 months of gearing up for today's special event when Perseverance will land. But as we get ready for that very special event, we'll take some time now to learn a little bit about Perseverance and the science instruments on board with NASA-JPL Solar System Ambassadors, Adam Hauser, Tony Rice, and Matthew Funke.
Welcome, everybody. I'm Tony Rice. I'm one of the NASA Solar System Ambassadors you're going to be seeing a lot of today in this description of what's going to be happening here later today when the Perseverance rover finally makes its way to Mars. I'm here with Matt, who will introduce himself in a second. We're going to be talking about some of the instruments that are aboard the rover. This rover may look very familiar to you. It's very much like the Curiosity rover. Actually shares the same spacecraft bus, which is the basic body of the rover, and the computers and the power systems and the mobility systems and all that. But these are just things that bring the instruments to Mars, which is really the important thing here. That's where all the science happens, is with those instruments. So we're going to share some information about a couple of those instruments today. And with that, I'll hand it off to Matt.
Hey, thanks, Tony. Hi, I'm Matt. I work as a NASA-JPL Solar System Ambassador, much as Tony does, so we can get the information about what we're doing with the unmanned space program out to as many people as possible. Honestly, I'm super excited about Perseverance. I've loved Mars ever since I was a kid and found out it was a real place and not just a thing they made in cartoons. It's super challenging trying to get something to the surface of Mars, gently, preferably, and in working order. And some of the things that they have and they plan to have working on this rover are absolutely phenomenal. It's taking us to the next level in terms of our exploration and in what we want to learn and what we want to see. The first instrument I want to talk about is SuperCam. This is the thing that grabs everybody's attention. Pictures, obviously, from any kind of mission are super important and have always been super important. People want to be able to see at a glance exactly what well, where we sent things to, and what they would see if they were there. That's the important thing about exploration, is giving people a sense of presence. And SuperCam, of course, is stuck up on the mast, like the cameras have been ever since Spirit and Opportunity, to give people a nice high vantage point from which to see the landing site, and of course, wherever the rover ends up going. SuperCam is an upgrade on Curiosity's camera. Curiosity had a camera called ChemCam, and one of its capabilities that was really super important was the ability to sense chemical compounds from far away. It does this with lasers, which is just awesome. It can tell, it can fixate on something about the size of a grain of rice from 20 feet away and pick up its chemical composition. This kind of thing is important because obviously we want to be able to find out the chemical composition of the interesting things and focus on the interesting things. And we don't want to waste all of our time sampling every little thing, but it's also the case that the rover is kind of slow. It moves at the pace of a slow walk. And we want to be able to get a good idea of the lay of the land and the context from a geological point of view before we figure out what we want to investigate in particular. You can basically analyze, even though it can focus on such a small area, it can analyze the chemicals from a good 12 meters away. So that's what, about 40 feet. It's really kind of amazing and upgraded from the old camera. It also has the ability to zoom, which the old camera did not have. Could I have the next slide, please, Tony? Okay, the next instrument that's sort of towards the back of the rover has been abbreviated RIMFAX. That's a radar imager. And it basically uses ground penetrating radar to figure out what's going on underneath the rover. This is kind of exciting because it can tell all kinds of things about the composition underneath, whether there's lava flows underneath, or as I'm sorry, Tony, I'm going to have to ask you for clarification on this. Was this Mars Polar Lander or Phoenix that dug up near the surface and found ice just barely underneath the surface?
I believe that was Phoenix, and it was really cool because it has kind of a looks like a backhoe, but a miniature backhoe that we put on Mars. You know, dug down into that Martian regolith, the Martian soil there, and immediately found snow. Immediately found carbon dioxide, frozen carbon dioxide. And the neat thing was we left it there, and it sublimated away. It turned from that solid into the gaseous carbon dioxide that makes up the atmosphere that I'm going to be talking about in a moment. So yeah, this is going to be another exciting experiment.
Oh, absolutely. And I don't want to take away any of your thunder. But obviously, one of the things we want to know is where else is this ice? If it turns out that there is ice or even briny liquid water flowing underneath the surface, RIMFAX should be able to find it down to I'm trying to remember the depth, about 10 meters under the surface.
Sounds about right.
Yeah, it's capable of basically, when you want to do geology, you want to get an idea of not only what is on the surface, but of course what's going on directly underneath, whether it's something that was recently buried or something that is being pushed up to the surface. Mars is not as I'm going to say as geologically active as the Earth. We don't really have direct evidence that it is geologically active at all. It may be small enough that it's completely cooled and doesn't have the molten interior that drives the things like tectonic activity on the Earth. But we also found some really tantalizing evidence a few years ago of methane on the surface. And the only things we know of that cause methane are life and geology. And it could be some third thing that we know nothing about. But regardless, these are things we didn't know Mars had. And regardless of what we find out it's going to be plenty interesting and fascinating to find out what's creating this methane and how much of it. More recent measurements have seen the methane disappear. So is this a kind of thing that is sporadic? Is this the kind of thing that's regular? It comes up at regular perhaps seasonal activity, or something else bubbles up from something that happens underneath the ground? We don't know. And RIMFAX will begin to be part of the process in piecing together some of the answers that we might want to find out what's going on beyond what we can see on Mars, just on the surface. Could you give me the next slide there, Tony? Thank you. The last one I'd love to talk about is Sherlock. Sherlock has the ability not only to look for compounds, but to look for organic compounds. And that's really kind of exciting. I should be careful to note that organic compound does not necessarily mean direct evidence of life. The only requirement you need to be an organic compound is to contain carbon. But we also know that there's some kinds of compounds that form as a result of fossilization. The most recent explorations with Curiosity have found really good, solid evidence that Mars was warmer and wetter in the past than it is now. These look like the sort of circumstances that might be conducive to the formation of simple kinds of life. And whether we find evidence that things started to come together to create this kind of simple form of life, or that certain compounds or more complicated biological structures were put through a fossilization process, or whether we find nothing at all of the sort. These are very valuable answers, whether it's the kind of thing that we realize, oh, all we need are these set of circumstances and the kind of organic compounds that we associate with life are almost inevitable, or we find out that, well, it's not enough what we thought was going to be put together. Honestly, with Earth, we only have one data point about where life can form, and we're still piecing together what the environment on Earth was like 3.5 billion years ago when life began to form. So honestly, the more data we can learn about this, the more pieces of the puzzle we'll start to be able to put together. It has the ability to look into things with infrared spectroscopy and, I believe, X-ray, if I'm remembering that correctly. And of course, the ability to look at things with cameras and telescopes and whatever. This will be key in forming the kind of samples that Perseverance will be gathering, and hopefully will be collected by a follow-on mission to bring back to Earth and study with the much more sophisticated laboratories we have back here. I think that's just about all I want to say to summarize what these instruments are on my end. Let me get over to Tony, and he's going to talk about things that are much more interesting about what Mars is like when you're actually there.
I don't know about much more interesting, but certainly maybe a bit more easy to wrap your head around, your arms around. So everybody has an opinion about the weather. Everybody, when we don't have anything else to talk about, we talk about the weather. So let's talk about the Mars weather. This is certainly not going to be the first time we have put weather instruments onto Mars. We've done that with just about every lander or rover or whatever we have placed up on Mars. And that's because there's really two ways that you can tell a lot about the history of a planet. One is the geology, and Mark shared a little bit about some of the things that's going to be going on with the geology, and Perseverance big sister rover, if you will, Curiosity, certainly had a lot of those types of instruments that were studying the geology and the chemistry of these rocks, and also had a very similar instrument to MEDA. It was called REMS, the Rover Environmental Monitoring System, and was sending data back on a just about daily basis of the observations of things like temperature and pressure and radiation that was being felt at the surface of the planet. Well, this is an upgraded set of those instruments. This is called the Mars Environmental Dynamics Analyzer. We love acronyms at NASA. This is really a backronym, and you've seen that in some of the other instruments as well, where we come up with the acronym first and figure out how we're going to make the words fit it. So MEDA is an instrument that is handled by an agency in Spain, and a lot of these instruments are coming from international partners. Again, these instruments are what are riding on top of this rover. That's the whole purpose of the rover going there, is to take these scientific instruments there. So this Spanish instrument is going to be studying more of the planet's atmospheric science there. And you can kind of see in that photo on the right-hand side here what that looks like. Those probes, those, we call them booms, that are extending out from the mast, are arranged in such a way that not only are they able to measure temperature, they're able to measure wind, and the way that they're arranged, we can tell the direction that it's coming from. I'm really looking forward to this instrument getting onto the surface of Mars, because the similar instrument that was on the Curiosity rover was unfortunately damaged during landing. You're going to see the entry, descent, and landing video later, where the rover, which is about the size of a small car, it weighs about a ton, is lowered down on cables, 20-foot cables, before it touches down. And that is to give a good amount of separation from these rockets that are slowing its descent from 30, 40 miles an hour down to zero for that nice gentle landing. Well, during the Curiosity landing, there was more dust and dirt that was stirred up than was expected. It's the first time we'd landed anything this big. So we learned a lot from that, and these instruments have been improved a bit, and that landing has been improved as well. So it's not going to stir that kind of grid up. So I'm hoping that we'll have those instruments survive a little bit better this time. Curiosity's given us great data. We haven't gotten the wind data that we had hoped. Very similar set of these instruments was placed on the InSight mission, which is a lander that's located several degrees of latitude north of where Curiosity is. We're getting great data from it. The thing about Mars is you look at the pictures and it looks like a desert. And it absolutely is a desert by the definition of how much moisture is in the air. Deserts tend to be very, very warm. Mars is not very, very warm. It is several degrees below zero almost always. It can get above freezing and does from time to time, but for the most part, the average temperature is down around -90. Very, very cold place. These instruments help us understand what that environment is like. You can tell so much about the history of the planet just by watching over time how those things change. And MEDA is going to be helping us there. If you move on to the next instrument here, this is a perfect example of a background. They came up with MOXIE and then turned that into the Mars Oxygen In Situ Resource Utilization Experiment. Nice hard name. In situ is very important here. There's two different ways that you can study things, especially in meteorology. You can study them remotely, which we've got a number of orbiters that are circling the planet right now. MAVEN's one of them that's studying the atmosphere of Mars and trying to understand what happened to it. Mars used to be a very, very Earth-like place, we believe many, many millions of years ago, where there was a lot more atmosphere, so much atmosphere that it could support, there was enough atmospheric pressure there that it could support liquid water. So we've seen evidence of that revealed by Curiosity's explorations, that we know that there was liquid water there before. So that's the remote sensing that is happening with missions like MAVEN. In situ means in place, right there. We'll be able to measure the atmosphere and the chemical makeup of that atmosphere. But most importantly, we're going to generate oxygen with this. We're going to take that carbon dioxide, we're going to split it into its components, most importantly, oxygen. So when we think about when we can finally put people on Mars, we can finally put boots down on the planet's surface, one of the big things that we're going to have to solve, that we haven't quite figured out yet, is how to have them breathe. We can't take enough oxygen with us. We can't take enough fuel with us. So we're going to have to break up the regolith. We're going to have to break up that soil there on the planet. And we're going to have to break that carbon dioxide that makes up most of the planet's atmosphere, have to break that up into breathable oxygen. And with that, I think we've probably covered the basics of some of the most important instruments here. Max, do you have anything else to add?
Sure. Just to add a little bit to what you said about MOXIE, I think it's really important to point out that part of the reason we're gathering these samples and storing them now is because space agencies are getting geared up towards a more robust exploration of Mars. China says that they want to have a sample return mission in the 2030s, and manned missions to Mars are on the table. We want to be able to figure out what Mars is like and how the chemicals on the surface of Mars change and underneath Mars change before humans get involved. So capturing a pristine set of these samples is absolutely key to finding that sort of thing out. Beyond that, I think you've done you've done a great job. Obviously, this is a very exciting mission, and it's great to see all these things come together. Because honestly, finding out about these places is not just about finding out what they're like, but finding out what it would be like for us to be there in a permanent sense. And MOXIE is absolutely key to making that happen. Thank you very much for everything you've described.
Yeah, thanks everybody for tuning in. We've got some more information that'll be coming up after this from some of the other solar system ambassadors, and stay tuned for the rest of the afternoon leading up to the entry, descent, and landing.
All right, what a fabulous overview of the scientific instruments on board the Perseverance rover and of the kinds of science that NASA researchers and beyond will be able to take advantage of to help us learn more about Mars and the red planet and Mars's history, and maybe even a little bit of Mars's future. Really cool stuff that, I mean, for the first time, we'll be trying to answer questions about ancient life on Mars, in addition to all sorts of great scientific inquiries that we're going to have. For our next presentation, we'll be getting into a little bit about where the Perseverance rover is headed on the surface of the red planet. The head of the Astronomy and Astrophysics Research Lab at the North Carolina Museum of Natural Sciences is with us to use a very cool, very neat universe visualization tool called OpenSpace to give us a little tour of the Mars landing site. Dr. Rachel Smith is here with us. Rachel, hi.
Hi, Chris. How are you? Hi, everyone.
I'm great. It's such a special day.
It is a special day. Every day is special. Yeah. But
especially when you're landing on Mars.
It's extra special to land on Mars. Absolutely. So I can start sharing my screen if you're ready.
Yeah, I say let's jump in. I'm excited to learn more about, is it Jezero crater?
It's Jezero crater. And actually this program is going to touch a little bit on astrobiology, which is something I'm really excited about as an astronomer. And I study how planets form. I look at the early stages of protoplanetary disks and look at their chemistry. And I'm also excited about the software OpenSpace, which is a NASA-funded project. NASA funds science, as we know, but it also funds really awesome educational tools. And this is a project that's actually led by the American Museum of Natural History in New York. And I'm going to drive around. We're on their team, and I'm going to show you this kind of one of these programs about astrobiology using this tool. And I'll just emphasize that everything you're going to see is all based on real data. And so the imagery I'll show you of Mars, and also I'm going to show you a little bit of Earth. And here we're seeing the solar system and the orbits of the planets and these star fields. They're all accurate, and they've been put into big databases over decades. And so that's what's really neat about OpenSpace. And it is open source, so it's free and you can download it. And if you have a nice computer, a fairly decent computer can run it pretty well. So I'll just start off. The reason I'm showing you the solar system now is because in astrobiology, we think about, what life could be like beyond Earth. Could life exist beyond Earth? And when we think about these questions, we're also thinking about Earth as well. And we're looking back at ourselves and we're trying to understand, how did life start on Earth? We still don't have that answer. And what's the future of life in the solar system and beyond? And what's the future of humanity, our own species, in the far future, or even in the near future? We could think about that. So what I'm showing you here is just the orbits of the planets. So we have all 8 planets here. This is the orbit of Neptune. We have all 8 planets, and there's, in every system of planets, there's a region called the habitable zone. And that's defined as the region where a planet can support liquid water on its surface. And so for our solar system, we of course know we're covered in water, right? Earth is 75% covered in water, but there is water everywhere in the universe. And we're in fact really like a desert planet, because by mass, we're only about 0.6% water, even though we're covered with water. So there's a lot of actually opportunities for life beyond Earth, and Mars is one of those places. But Mars, unfortunately, is not really in the habitable zone anymore. And it was actually at one point, there was a lot of water on Mars, and we'll look at some evidence for that at Jezero crater in a few minutes. So this is the orbit of Earth around the sun right here. And my mouse is a little fast for me. You get a nice gaming computer and it's better than you. It's more intelligent. But I'm showing you the orbit of Earth. So the habitable zone in our solar system might touch Mars a little bit. Here's the orbit of Mars. Because there's some evidence that water could flow periodically on Mars now, but certainly not what it was like in the ancient past, where it was probably it could have been a lot like Earth. And there's a lot of question of what happened. We have some answers now from various missions of what happened on Mars, but it's still worth investigating life on Mars, even ancient life, to learn more about the origin of life in the solar system, to see if we could possibly not be alone in the universe. And any evidence for even past life that's not from Earth tells us that we're not alone. So there's some big questions we can have answers to, even by just exploring our nearest neighbor. So what I'm going to do is I'm going to zoom in with open space, and I'm going to zoom into Earth. And I set this up to go to a specific place on Earth. I know this is a short program and we want to get to Mars, so I'm only going to show you one spot on Earth. But just take a look for a second. This is our blue planet, right? And it is a really, beautiful place. We should take care of our planet. This planet is, and this is, we have a night side, of course, periodically, as we know. But this planet is our home, and it's the only planet now in the solar system that can support liquid water on the surface. Can we one day terraform Mars to support life? Maybe, if we figure that out, but that'll take a long time if it's at all possible. So I highlighted one spot, and we're going to get there. This is not very close to home. This is in Turkey. And the reason we're going here is because it has a lake called Lake Salda. And this lake, I put a little bubble on it so I'd find it, because I'm not an expert in geography, especially beyond my nearest neighbors. This is Lake Salda, and Lake Salda is what we call an analog region on Earth that we use to try to understand where to look for life beyond our planet. And there are many places like this on Earth. There's places with extreme life, like microbes that live in these boiling pots, in these mud pots in Yellowstone, and microbial communities that live under the ocean. But Lake Salda is particularly interesting because it has what we call these carbonates, which are this fine white line around the shoreline of Lake Salda. And it also has a delta here, a region where water had fanned out to create the lake. And what's interesting about Lake Salda is these carbonates were deposited by microbes over millennia, really, and they are studied as analogs of what we think could be in Lake Jezero, or the region that was once a lake on Jezero. We have data from the Mars orbiter called the Mars Reconnaissance Orbiter that there are magnesium and carbon or carbonates, which are basically geologic features that form in the presence of water and could form by microbial life. And so what's interesting is that this is one of the only lakes on Earth that has these exact deposits that match the spectroscopy that's been studied over Lake Jezero. And so this is an analog lake, and scientists have gone to Lake Jezero to try to understand what they might find. Gone to Lake Salda, in Turkey, to try to figure out what they might find on Jezero when the orbiter gets here. These blocks, by the way, you see it's open space is trying to pull in a lot of data. So sometimes you see data missing, and I'm zooming in quite a lot. So sometimes we don't have all the data we want. But this is just a little flyover of Lake Salda. So, okay, so that's an analog. So we'll come back to this idea of filling this lake, Jezero, this crater with water at some point in Mars's past. So I'm going to zoom out now. I'll leave my little bubble because it won't matter. We're going to get pretty far from Earth pretty fast in a minute. So one thing that's fun about open space is you can travel faster than the speed of light. We're going to go to Mars in about, 10 seconds. So let's go do that. We'll go to, in fact, we can get there pretty, I'll just focus on Mars. I'll just type it in here. Oops, I didn't type it in. Okay. All right, so that's going to direct me, and then I'm going to fly to Mars. And we know Mars. We have a lot of data on Mars. We have a lot of data from the orbiters on Mars. We've sent rovers to Mars. And what I'm going to do is I'm going to turn on, let's see. I'm going to get to, we can just take a quick look before I turn this on because it's going to take us right to the crater. But basically you can see with, we have all these data sets, by the way, these stripes on Mars are essentially high resolution data sets. So when scientists want to visualize planetary surfaces in high detail, they have some regions that have really high resolution data. And so these are, if we zoomed into any of these regions, we'll see some really awesome imagery of Mars. But we see these impact craters. And one thing I'm going to show you is that, as you all probably, many of you know, we have asteroids in our solar system, and they hit planets. And we have remnants of these hits, a few on Earth, about 150 impact craters, about 40,000 impact craters on Mars. And the reason is that Mars has preserved its impact craters much better than Earth because Mars has a very thin atmosphere and more bits of asteroids can actually make it through and impact Mars. And Jezero happens to be an impact crater. In fact, it's 2 impact craters. But before we get quite to that crater, I'm just going to turn on the Mars crossing asteroids, which I added in here. So all of these asteroids are called Mars crossing asteroids. There's about 18,000 asteroids here. These asteroids are in the same, the trajectories of these asteroids have been studied to show that they can impact Mars. They may impact Mars at some point in the future, and Earth has crossing asteroids as well, just like these that will hit Earth, could hit Earth in the future that we want to be aware of. And one of these asteroids, at least a few, made the region of Jezero crater. So let's go to that. Since we don't have a whole lot of time, you can zoom in. We have this programmed. Who knows? Oops. Okay, there we go. At least I have my ellipse. All right. So we look down, we see basically an impact crater, and you can see the banks, this hillside, which is essentially the rim of where this impact occurred sometime in the past. It could have been a few million years, perhaps. And you can see here, this is actually, we have to zoom in a little closer. Let's get to it. And I'm going to go to Mars now. Oops, sorry. I know my driving is, in a longer program, my driving isn't so terrible. I mean, I have less time to fix it, I guess. But here we go. So as soon as the data loads, you'll see. But basically, this is a water channel. And just like I showed you at Lake Salda, and there are plenty of deltas on Earth. There's the Mississippi Delta, which is a very famous one. Water flowed in a river and made this lake possibly a few million years ago. You can see various other impact craters that fell within that, but essentially this was filled with water at some time in the past. And we know that lakes are teeming with life typically on Earth, even microbial life. So even lakes that are hostile to life, even bodies of water like the Dead Sea, there are, which has a lot of salt, there's still life that lives there. And so it's really, this was why Jezero was chosen. It was, it's a difficult terrain to land, but it's not too hard for NASA. There's plenty of other regions on Mars that they want to visit, like the Big Canyon, Valles Marineris, and that's a little trickier to land in. But Lake Jezero is this crater is actually a really exciting place because of these banks and because of the sediments that are in the mud and this evidence for deposits that could have been due to life. And we don't know. I mean, so that's the big question, is that when you hear that there was water on Mars, when astrobiologists hear this, they get really excited, because where you hear where there's water, there could be life. All life as we know it needs water. And so just remember, maybe Jezero crater looked a little bit like Lake Salda in the past. Is an image I just overlaid of Lake Salda, so it had water and maybe evidence for life. These are really interesting. These are called stromatolites, and these are layers of microbial deposits over many, even they could be millions of years old if they're fossilized, but a few thousand years. And these are actually they're like stacks of microbial mats, and they're very similar in their makeup as, you know, the type as the type of deposits that could exist. The same microbes can make these deposits that we see evidence for at Jezero, as well as other regions on Earth. And so microbes could exist somewhere in the sediments, and maybe at one point, actually, it looked like this on Mars. We don't know. And we think about water on Mars, and we think about, well, where are humans going to go next? And something I'm very interested in is thinking about the future of human civilization. And we can't get very far in our travel. We have chemical rockets. We have an exciting time now. We're starting to send astronauts back to space with our own rockets through commercial collaborations with NASA. But where are we going to go for any long term? And the question is, can we transform the atmosphere of Mars to support water for the long term? So we don't have to, so if we ever, when we ever get to Mars, probably in a few decades, maybe, will we ever able to transform this planet to be like a planet Earth with liquid water on its surface? And so some of these concepts have been developed thinking about what would a future habitat look like on Mars. And so this is one sketch I like. It's obviously a rendering of little bubble habitats, and they've been actually studying this type of accommodation in isolation. There are places on Earth where they put people for long periods of time, in Hawaii and some other regions where other places on Earth where they've tried to study how humans can exist in these closed habitats. But eventually, we want to know if we can modify this environment to support life and transform it. But that's a very hard thing to figure out how to do. And we certainly aren't doing very well with our own planet, one could argue. And finally, just to think about what would it be like on Mars, I like this rendering of, you know, maybe one day we'll have an ocean on Mars. And these are just some of the things that roll around in my head. And when I teach my classes, what could we think about? But you can zoom in to this, just getting back to some of the actual current science. You could see this is all evidence for there's wind erosion, and there's evidence of this shoreline here. And certainly we know that water once flowed here. And so the rover, it'll start here and it'll rove around to these craters and then back towards this rim of the impact crater and look at the sediments, and hopefully hopefully find something that's interesting, maybe signs of ancient life. We don't know. As scientists, we can't predict, of course, or say we're going to find one thing or another. We just hope for exciting data and then analyze what we get. But it is an exciting day to get to Mars. And remember that we have rovers on Mars already and have found still compelling, there's a lot of evidence for water flow on Mars, no evidence for life yet on Mars anywhere beyond our own planet. So I guess, I wanted to leave time for questions. So I don't know if there are questions yet. If Chris is there, you can tell me, or I can keep exploring here with my program. This is just a brief overview I was gonna do. Are there any questions so far about Jezero or water? Are people still there? Hello?
I'll give folks just a minute to get their questions in.
Oh, okay. For a second, I was worried that nobody was there.
We all left.
Right.
No, we're all here.
Okay.
No, Rachel, this was fantastic. The open space imagery is just beautiful.
Oh, it is. It is. And I'll just say, you need a pretty good internet connection to share this. So I want to impress upon people that while I have as good internet as I can, I'm in my office today versus my house, which has less good internet. It is much nicer when you have it on your own computer. So this is to give you a sense of what you might see, but it'll look nicer when you're not seeing it through Zoom.
So if folks are exploring using open space, are there certain things that they should say if they're doing like this right now, they're flying around the surface of Mars? how could they potentially identify sites that maybe were ancient rivers or lake beds?
Yeah, that's a great question. So I know, so as far as just going there immediately, so what you can do with the program, I'll just say, is in a beta phase, meaning we're still developing it. It's funded for another 5 years, which is really great. So as far as being very user friendly and set in the sense of I want to go here and you can just click a button, you kind of have to set up more or less where you want to go. And the way I've done this, and it's one way to do it, is you look up. So if I know I want to go to certain places, I look up the coordinates online, and then you can code them in to the code. There's also an easier way to do that with an Excel sheet that comes with the open space code. And all of this is a good question. I can't see the chat. I don't know if the open space people are here, but they often mention how to do this stuff. But openspaceproject.com is the website, and there are tutorials on how to add bookmarks. But what these are called bookmarks, and what I've done is I've added these in that I'm showing you in the menu. I've added these in to my open space programs, and they've been coded in with their coordinates that you can just find even on Wikipedia or something. I mean, then you can check them, because then you can compare with different images from NASA or somewhere else. So it's not like Mars is mapped out yet with all the bookmarks, but that's something to think about. So you can pick where you want to go and then have them coded up. So I could go to any of these places on Mars right now just by clicking them, and then they, you can fly over there. I won't do that in case anyone has a question on Jezero, but it's available.
So let's see. One of our viewers wants to know if there's any sign of the joint Earth alien base.
Okay, who asked? No.
Yeah.
I don't know of that base. The answer I'd say is no, he isn't. Was that it? Yeah.
It's not on there yet. Can we get in real close to the exact point that we expect Perseverance is going to land?
Yeah, so that's here. So we don't know exactly yet. NASA has an ellipse because they can't tell you exactly that the rover is going to land in this exact point. But I would just say be impressed by the fact that they can get it to this. I mean, Mars is it's millions of miles away, and able to even pinpoint this close. This is a few kilometers in diameter. And so it's not very, it's not a very large ellipse. It's not going to go out, hopefully, into these hills over here. But it'll probably land, they hope it lands right about where this line ends. And I can zoom in there too again.
Natalie on Facebook is curious if we'll be able to see the surfaces live when the rover lands.
You mean as it's landing?
As it lands or right after it lands?
Well, so I'm not sure how NASA's going to share the data. First of all, it's 7 minutes between information of it actually landing and us on Earth, anyone on Earth knowing that it landed or didn't land. Hopefully not. Hopefully it does land. But it's that 7 minutes of terror that you hear about, and that's just because it takes 7 minutes for any signal to come, for light to travel to us from Mars. So all images have to be processed. So it will take a while, I imagine, to see actual images of Jezero sitting here on the banks of, Perseverance sitting here on the banks of Jezero. I don't know how long. It'll probably take at least a few hours once they start processing it. But it's not going to be an immediate, here we go, we landed. It's going to be, they'll know it lands through signals that come back from the rover, that it didn't just disappear. But a really pretty processed image of the rover won't come through just yet, just right away. I mean.
And then Lauren and Addison were asking about a black line that was on the screen. So I think when we were zoomed out a little bit earlier, you had the landing ellipse outlined in a big circle, right?
This line here, right out in the distance right now. I was just zooming into the rover so you can see kind of what it hopefully will look like. But yes, the thick brown line that you see that looks kind of painted on, that's just the landing ellipse overlaid around the crater. So here, hopefully the crater lands here in this really nice spot. and eventually we'll get a picture of it. There's some really excellent. You're going to be impressed, I think, when NASA sends back these high resolution pictures. They're really quite spectacular. What we can see on Mars now. So
I'll certainly be looking forward to seeing some of those early images.
Yeah.
They're always stunning.
Oh yeah. Here, I'll just leave it there. You can see the asteroids and the landing trajectory.
Beautiful. All right, last one here that I think would be a good question for you. Why this part of Mars and not another?
Yeah, so again, it's sort of this idea of what do we want to do on Mars? And the main question is, did life exist on Mars right now? This is the big question. And does life exist now on Mars? Which, of course, if it does exist, would probably only be microbial under the rocks where there's some water that's consistently there. Jezero was chosen because it clearly had water in the past. We see this from the terrain of the carved river channel that comes through the crater, and by that ring of carbonates of the magnesium and carbon and other minerals that minerals containing these elements that are in the crater that we already know about from the orbiter around Mars. And so the Mars Reconnaissance Orbiter has sent back a ton of data that says this is a good place to look. We can see that there was water that flowed here, slowed down, and made this delta and filled in this crater, just like it does on Earth and does on other terrestrial surfaces. So at one point, Mars could hold on to its water. Water filled this area, so it had water. It's not too difficult right now for NASA to land on it through the current technology to land in this region. It's not so far from where Curiosity landed, the other rover. It's like 200 miles or so. And so it's a fairly safe region to land your rover. It had water, and it has suggestions that life could exist or did exist there. And again, just saying that this is all how science works. It doesn't mean life does exist on Mars, and it doesn't mean we're going to find life on Mars. It just means this is a really good place to look. I know everyone wants there to be life on Mars.
Mike wants to know about the lower gravity on Mars and its effect on the human body.
Yeah, that's a big thing, right? And so they're studying the effect of microgravity right now with astronauts who are on the International Space Station for long periods of time. So you can read there was I think it's Scott Kelly and his twin brother are both astronauts. And I think it was Scott Kelly, if I'm not mistaken. Scott Kelly was the one who stayed in space for around a year on the International Space Station. And they studied the effect on his body with microgravity, which actually there's less gravity there than there would be on Mars. But and even with the exercises they do and all of that, you can read, it's really kind of fascinating. It's a little bit, it shows how far we have to come. We're not designed to live in microgravity. And he talks about the physical effects of coming back to Earth after being on the International Space Station. First of all, he of course has to be taken off with a stretcher. He can't walk right away at all. And then there were other effects, like he was sick a lot. And he wrote, if you Google this, Scott Kelly, and they compared the effects on his body with his twin brother, who didn't spend as much time in space. And there was some initial report that the genetics were modified, but then they rolled that back, that was actually not something that happened, that it actually affected his genes, but it certainly affected him physically. And that's something to really think about, is how are we going to survive, not only forget terraforming, but just existing, if we can get there without being irradiated to the point where you're not even going to survive very long at all. Once you get there, it's also, how do you exist there without gravity? You'd have to have some kind of way to simulate some gravity, or because 30% gravity is not enough, I think, there's studies about this, of how this affects the body, but we're not designed for that. We're not designed to live under the ocean, and we're not designed to live on Mars. But eventually, if we get to Mars, there will be the first human born on Mars, will be a Martian. And then we have a whole other story to tell. That'll be my next talk of what to do with your Martian.
Right.
So,
well, in the meantime, we'll look forward to seeing some of the real images from Perseverance. And everybody, you can look up Open Space online, download and explore the universe more with all the great tools that are there. Yeah. Rachel, thanks for being with us for today's Perseverance landing event.
Thank you. This was a lot of fun. Thank you all for coming.
Excellent, excellent stuff. If you've just tuned in, everybody, or just tuned in the last few minutes, welcome to the North Carolina Museum of Natural Sciences Perseverance Landing event. We are celebrating Mars 2020 with, we just finished celebrating with Dr. Rachel Smith, astrophysicist at the museum and Appalachian State University. And we have a whole crew of local NASA-JPL solar system ambassadors who are bringing us insight and knowledge. And for our next presentation, something fun that you can do at home to celebrate NASA's Mars 2020 Perseverance rover. Let me introduce Sarah Taylor, another one of our NASA JPL solar system ambassadors. Sarah, are you here with us?
Hey, Chris.
Hi, Sarah. Thanks for being here. Now I see you.
Yeah, there we go. All right.
So I understand you've got a fun craft or activity for us.
Yeah, I do. So the first thing I will do is I will share my screen, and my share screen is a little different. Instead of seeing a PowerPoint, you are going to see, hopefully, my table.
Ooh, very fancy.
Yeah. So have with me my little Mars. It's going to help us. And so what our activity is we are going to make a little model of a rover out of materials you can get around your house. So I'll go over the materials first, and then we'll get started. And during parts of this, I will ask you guys, the audience, what you would like to have us do to our rover, what parts we should add, what things we should be thinking about. And so when I ask those questions, Chris will be watching all the chat, and he will let me know what decisions you guys make. So everyone needs to get their engineering hats on and be ready to build along. All right, so if you want to follow this along at home, these are the things you'll need. One piece of cardboard. This is 6 by 6 inches. 2 pieces that are 5 by 5 inches. 2 pieces of hard candy that have a hole in the middle. A sharpened round pencil. So this is round. It's not one of the hexagonal pencils. It is a round pencil. A regular old drinking straw. Some rubber bands. I have a whole bunch of different rubber bands here. The different ones you have, the better options you'll have to do different things to your rover. So that's why I have a whole bunch here. I have a bunch of skinny ones. I have some thick ones. I have some ones that are really big and some that are really tiny. And then for extra supplies, you'll need a pair of scissors, some tape, a cup or a mug so you can trace a circle, and last but not least, some coins. All right. So does everyone have their engineer's hats on? Are we ready to go? All right. So
let's do it.
Yeah. All right. So the first thing we're going to think about is we're going to think about some previous rovers, because that's how NASA does a lot of their missions and projects. They base them off of ones that they've done before. So this is a picture of Spirit, which is one of the earlier rovers that's on Mars. And so we could look at kind of what it looks like. So it's got the big wheels on the bottom, and then it's got a platform where it can carry all of the science equipment. And it has some sort of way to power itself. So those are the basics of kind of any vehicle. Is it needs wheels, it needs some sort of base to hold everything together, and then some sort of way to power itself. We also have, I have a little model of Curiosity. It's a little die-cast model. You see it's built the same kind of way as Spirit. It looks a little different, but the ideas are still the same. It's got wheels, it's got a little base that all the parts sit on, and then it has some way to power itself. Right. So to start our building, we're going to take our 6 by 6 square of cardboard. And if you look at your cardboard, I'll try to hold mine so you can see it. Do you see how there's lines in the cardboard? That's called corrugation, and you're going to want to orient that in a certain direction to make the model make easier. So you want to have the lines going up and down. So see, my lines are going away. They're going up and down away from me. So hold your cardboard going that way. I'm going to draw on this one so you can see where the line's going. So on mine, the line is going this way. It's going up and down. You're going to take your cardboard and you're going to fold it kind of along two of these lines into thirds. And fold it real tight. Really fold it over. Okay. So this is going to be the base of our rover, our little rover body. All right, so we can set that aside for now. Now on to our wheels. So your wheels could be a lot of different shapes and sizes, but obviously the most practical shape for a wheel is for it to be round. So to get our round shape, we are going to use a cup to trace our wheels. So put your cup in the middle of your piece of cardboard and draw all around your cup. And repeat that on both pieces of cardboard. And then once you have two circles drawn on your cardboard, it's a little hard to see on mine, but I can see it. You're going to cut it out. You want to try to cut it out in as neat of a circle as possible.
And if anybody is crafting along at home, drop a note into the chat on Facebook or YouTube. Say hi, let us know that you're working on it.
All right, so I've cut my two wheels out and I'm going to kind of look at them before I move on. So like this wheel, do you see how this one has like this little point right here where I didn't quite cut it circular? I'm going to go back around. I'm going to trim that off. So I'm going to kind of look at both my wheels and just trim them to make sure they're nice and circular. This one looks pretty good. I think maybe just trim right here just a little bit. Okay. So we have our two wheels and we have our body. Okay. So now we have to get our wheels attached to our body. And this is what our pencil is for. Now this next part could be a little tricky. So if you're making this at home, you might want mom or dad to help you out with this. But what you're going to do is you're going to kind of look at it. This could be a little tricky, but you're going to take your circle and mark the center of each circle with like a dot. Try to just look you best as you can where you think the center is. That looks pretty centered to me. Okay. Then you're going to take your pencil, and this is why it needs to be a sharpened pencil. And you're going to poke it through the cardboard. So you want to kind of watch your fingers, but it'll poke through pretty easily. Just kind of twist the pencil back and forth real gently, and it'll poke through. There we go. Okay. And then you're going to pull it back out. And then you're going to do the same thing to the other wheel. There we go. Okay, so now we have two wheels, holes in the middle. Now we're going to look at our rover. We need to put the wheels onto our rover. So we're going to put them on the same way. We're going to poke holes through our cardboard. So this could be a little tricky. You want it to be as straight as possible. So what I'm going to do first, I'm going to look at mine. And the wheel is going to go through the side like this way. So I'm going to mark on my sides where I think like the halfway point is. So there's my halfway point on this side, and there's my halfway point on this side. Okay. Then I'm going to poke one hole through one side. It could be a little tricky to poke the holes. You might have to move around where the pencil is, because if you get in the middle of one of the corrugations, you're trying to poke through like 4 layers of cardboard, and it can be really difficult. And I'm going to do the same thing on the other side. You want the hole to be about in the same place. So when you fold the cardboard back together, you could stick the pencil through the 2 holes. Pencil through our holes. My holes are not quite straight, but that's okay, because cardboard is pretty forgiving. So what you can do is, this hole's a little off for me, so I'm just going to move it and poke a new one. And this is also all part of engineering. You know, something might not work the first time you try it. You might have to try something different to make it work better. All right. So now that we have the holes in our body and our wheels, we're going to attach everything together. So this is kind of like making a sandwich. First, wheel number 1, push it almost all the way to the end of the pencil. Then grab your pencil, poke it through the rover, and then put on wheel number 2. And you want to kind of move the pencil around and make sure that you think it can move smoothly in the cardboard. So mine feels pretty good. So now we have to attach our wheels, because we need to make sure our wheels don't spin by themselves. They need to spin at the same time as our pencil. So what we're going to do is we're going to use some tape to do that. So I have my tape right here. And the way I like to tape on the wheels, I'm going to try to tip it so you can see it, is I like to put a piece of tape going up the pencil and then down to the wheel. And then do the same thing on the other side of the pencil. Tape down the pencil and onto the wheel. So you kind of get like this little, like the tape goes like, it's like 2 little L's on either side of the pencil. And then to make sure it really stays on, I take another piece of tape. And see how I have this loose tape around here? I'm going to take this 3rd piece of tape and I'm going to wrap it around the pencil this way. You want to make sure the tape is really on there. So really press it down on your rover. Then you're going to do the same thing to the other wheel. How's everyone looking, Chris? Are people building along?
They are. I'm going to give a special shout out to Christina, who's got a quote, happy boy crafting along with us. And let me see what's happening over here on YouTube. And James, as well as the Lobdell family, they're all crafting along with us. And Sarah, I'll say your crafting ability is phenomenal.
All right. All right. We have
Maybe I should say you're a great engineer.
our, All right, so now we have our body and our one set of wheels. But it's going to kind of be funny if you try to drive it with only one set of wheels, right? So we need a second set of wheels. So that is what our little candy is for, is to make the second set of wheels. But this is one of the parts where I need you guys' help, because there are 5 different options for the color of the wheels. Not that the color really matters, but it's kind of fun to get to pick what color. So these are the 5 colors we can pick. I have a question. What color should our wheels be? Red, orange, yellow, green, or purple? So type in the chat and let Chris know what color you think the wheels should be.
So I'm going to keep an eye on this. Let's see. I'm thinking if you had red wheels for a Mars rover, they wouldn't show dirt so poorly, right?
Mm-hmm.
Mars is red, so if you had red wheels, they would just always look red. You'd have a nice clean looking rover.
They would, and that's actually really funny, because the little Curiosity model I have here, which I'll bring up, try to bring it close to the camera so you guys see it. They actually made the wheels where they're 2 colors, and so they have like Mars dirt on them, because the wheels are normally black, but they die cast it where it has this like Mars dirt on it, like it's been driving around getting all dirty and dusty, like your car does right now when it's winter and you get the salt and ice the salt all over your car, and your car turns funny colors.
That's so cool if they did that.
Mm-hmm.
So let's see. I've got some votes coming in.
All right.
And it looks like right now I have the most votes for the color green.
All right. We will do green wheels. So I have my green candy here. I have to get it out of its little packet. 2 green candies here. So what I'm going to do is I'm going to take my straw and I'm going to put my candy on the straw. And you kind of push it towards the middle, because what we're going to do is we're going to do stuff with the ends of the straw now. So we're going to take the end of our straw and we're going to fold it like 2 or 3 times over itself. So it makes this nice little like fat end, because this way the candy can't fall off. So once you have your straw folded a few times, you're going to put some tape around there.
And Sarah, I just want to point out, we have some engineers in the chat who, instead of using the candies, they didn't have any candies. So this is brilliant. They're using red wheels made out of Baby Bell cheese wax.
That's such a good idea. I meant to say that at the beginning, that that's kind of another part of engineering, is figuring out things, is problem solving, and figuring out what you might have that you could use, that because if you don't have all the exact materials that you need, and kind of working with what you have. All right. So once you have it taped, you should have 2 candies trapped on this straw, so they can't get off. They're kind of stuck. So this is going to be our front set of wheels. So what we're going to do is we're going to take our rover and we're going to flip it over. Now, before we put the wheels on, we have to do one more thing, because this could get in the way of where you put the wheels. At the front end of your rover, so not the end by the big wheels, but this end where there's no wheels right now, you're going to cut 2 little slits in the cardboard. So see how I cut 2 little slits there? So there's like this little flap here in the front that has 2 slits in it. Okay. Now, once you have those cut, you can put your front wheels on. So while it's still flipped over on top of on its back, kind of, you're gonna set your wheels, your axle with your 2 candy wheels or 2 cheese wheels on there, and then you're going to tape that down. So you're going to put like a piece of tape right here across, and make sure your tape doesn't cover these 2 slits. That's why I put the slits in first, so I know where to not put my tape.
It looks like we've got another group of engineers in the chat who are using sewing bobbins as their front wheels.
Ooh, that's another really good idea.
And other materials like wooden skewers or yarn in place of the plastic straws.
Mm-hmm. And this project is also, as you could tell, this is a great way to recycle materials. You could maybe, save a straw from the less, like when you went to like a fast food restaurant and got a drink to go, you could save the straw. All my cardboard is cardboard from like a package that I got.
Excellent points.
Yeah. All right. So now we kind of have a little vehicle now, don't we? Kind of roll along. Kind of doesn't roll very well, but it kind of goes. But one thing it's missing that the rover has is it needs something to power it, make it go. So that's what our rubber bands are for. So you're going to use a rubber band to connect this back wheel and axle to the front of the rover. So what I found works best is 2 smaller rubber bands. This is like a pretty small one. I'm going to try to hold it kind of flat so you can see it. I have these like these small ones. If you see, I'll put a bigger one down next to it. There's like these big ones, and I have these tiny ones. I'm going to use the tiny ones because I find those work better. The more like stretch you can get makes it go a little better. So I'm going to take 2 of these little tiny rubber bands and I'm going to tie them together. So the way I'm going to do that, I'm going to hold one in one hand, take my other one. I'm going to put it through, and then I'm going to put the other end through the loop I just made. So now I have 2 of them looped together. We got a little figure 8. And then I'm going to connect those to my back axle. So I'm going to take the rubber band, put it under the axle. And see, I have this big loop over here in my right hand. Oops, I let go of it. There we go. Now we can see it. I have this big loop over here in this hand. I'm going to take my hand. I'm going to grab the tail of the rubber band and pull it through. So now my rubber band is tied around this axle. Now I'm going to take the loop at the other end, this empty loop. I'm going to pull it forward, and I'm going to feed it through those 2 slits I put at the front. And see how it's not really tight right now? I want to pull on the rubber band until it's tight against the bottom of the rover. Oops, let me make sure I'm in the camera frame. All right. So now I have the rubber band, and it's all powered up. So now it has a way to get some power to spin these back wheels. So when you turn the pencil, wind it up, the back wheels spin. All right. So let's give our little rover a little test drive and see what happens. Let me move a couple things. We have a little bit of room to run our little test track. So I'm going to take my rover and I'm going to turn the pencil. I'm going to keep turning it, and you should see the rubber band start to wind up around the axle. See how it's starting to wind up around the axle? Once it's all nice and wound up, you should be able to really feel it, the rubber band pulling on the pencil. I'm going to set it down. I'm going to let it go. We're going to see what happens. Let's see what happens. Oh, it kind of spun, but it kind of skidded around. Didn't do a very good job of driving. It kind of slides and is slippery. And so if we look at it, our cardboard is kind of slippery and slidey. It just kind of slides around the table. So I think our rover needs something extra. I think it needs some tires to make it drive a little better. So we're going to put some tires around our cardboard so it can grip the table better and keep driving, like how your car has tires so it can grip onto the road and doesn't go sliding all over the place. So we have 3 options for tires. Which rubber band should we use to put around the tires or the wheels to make them grip better? Should we use one thin rubber band? So I'll show these ones this time as I talk about them. So should we use one thin rubber band? Should we use 2 thin rubber bands, kind of just next to each other on the wheel, or one big thick rubber band? And if you want some, like, if you want to look, I'll hold this up closer so people can see it. If you remember how thick our tire is, maybe use that to make your decision. So Chris is going to be looking in the chat and he will let us know which tire we are putting on our rover.
All right, I've got the chat pulled up. Folks, let me know what you think, which kind of tires we should use. I'm not really too sure about this one. I feel like there's strengths and weaknesses to each one of these, like a really thick, heavy rubber band would weigh a lot, and maybe that could impact how well the wheels work. But maybe small rubber bands wouldn't work as well because they wouldn't have enough grip on the table. Yeah,
that's a good thing to think about. And like I said, think about your car and how big are the tires in relation to the wheel that they're sitting on? Are they bigger than the wheel? Are they smaller than the wheel?
All right, let's see. Coco says one thick rubber band. Rushin says one thick rubber band. Hugo says one thick one. With another vote from the Kreshe family. They vote for one thick, I hope I pronounced your name right. We vote for one thick rubber band. Over on Facebook, the Smiths are saying one thick one. Only Stephanie is saying the thin rubber band so far. We've got the most votes for the thickest rubber band.
All right, so we got our thick rubber band here. I got one of these really thick, like office ones. And so we're going to put it around our tire, kind of like you'd put tires on a car. It's going to go around the entire outside of the cardboard wheel. And it could be a little tricky to do this. So if you're doing this at home, if you have someone to help you, it can be easier if someone holds the rover while someone else kind of stretches the tire on. And if we look at the actual rover for Perseverance, so it doesn't have tires in the same way like your car has tires, like that rubber thing that goes around your wheel. But it has wheels that have like patterns pressed into them, so it still has grip on the ground.
Are Perseverance's wheels made of rubber bands?
I think rubber bands, I think the rubber might do funny things in space. I think that's maybe why they don't use rubber. That would be a fun thing to find out, though. All right, so now we got our wheels on. Let's test this guy again. Let's see if it goes any better. We're going to wind him up again.
We'll call this 7 seconds of tension.
That would be a good name for this rover. And also, if you have a hard time, I'm going to tip my cheeks. If you have a hard time with your rover where the cardboard is kind of splaying out and hitting into the wheels, what you can do is you can put a piece of tape over the top here, and that will kind of keep the top together and it won't spread open as much. All right, let's try trial number 2. Let's go. Whoa, it went that time. So that adding that grip really did help it, didn't it? All right, we're gonna wind it up again.
Awesome.
Let it go again. We'll see if we can, it's hard to tell at this angle, but one thing that sometimes these can do, especially depending on how big your back wheels are. My back wheels are kind of small, but the bigger the wheel is, what can end up happening is your rover will flip up on its back wheels, kind of like a horse when it rears up on its back legs. And so there's a way you can fix that problem. Because as you probably can guess, your rover is kind of, I'm going to hold it up in my camera so you can kind of see it. It's really unbalanced. See how heavy it is? The back is way heavier than the front. So to kind of give it some more balance and make sure it can really ride straight, we're going to put some weight on the front of our little rover. So that is what the coins or the washers are for. So this is our last question. All right. Which coin do you think we should use to balance our rover, to balance the back and the front? So we have a penny, a nickel, a dime, and a quarter.
Penny, nickel, dime, quarter. Interesting. These all have different weights and thicknesses.
Mm-hmm.
Be interesting how they would all impact the rover. This would be a good science experiment for everyone to do.
Mm-hmm.
You could try them all.
Yeah, you could test them all. And this is another thing with engineering and science is testing it. And if it doesn't work the first time, you can do something else and change it and say, oh, I don't think that worked. I'm going to use a different one this next time. And then you can try it again. And also because these are you put them on at the end, they're really easy to take off and change and try a different one.
All right. Right now, I've got 2 votes for the quarter.
Alrighty.
3 votes for the quarter.
Yeah, the quarter I think is a good choice because the pencil is actually really heavy. Surprising, you wouldn't know it because it doesn't seem very heavy, but the pencil is pretty heavy. So the way we're going to put our weight on the front is we're going to flip it over, and right here, right behind the front wheels, we're going to stick a piece of tape to our coin of choice, and we're going to just stick it on. Just kind of gently stick it on so you can peel it off later. All right. Now we kind of have a little rover. Let's test it one more time, see if it rolls a little better now that it has some weight on the front. Oh. Yeah, that seemed to roll a lot straighter that time almost. It didn't just kind of fly off the table.
Very cool.
And I will show real quick, just as what I was talking about, if you're having problems with the top, just kind of put some tape right here over the top. It'll hold the top together so it doesn't hit the wheels. All right, so that is our little rover. I hope everyone had fun building along.
We had lots of folks building along and helping us guess. Sarah, thank you so much for sharing your engineering expertise with us and teaching us all how to make our own rovers.
Mm-hmm.
Sarah, thanks for being with us for our virtual landing event. Really appreciate it.
All right. Bye, guys.
Bye, Sarah. All right, everybody. Now I'm going to bring on my co-host back into the show, NASA-JPL Solar System Ambassador, Alan Rich. I can't hear you, Alan.
Okay, I unmuted myself.
Yeah, you just had to yell louder.
Okay, got me? Okay, the next presentation we've gotten for you, I'm joined by Doug Lively, a NASA-JPL Solar System Ambassador, also with the Raleigh Astronomy Club. We're going to talk about a thing called EYES. It's a NASA-JPL app that you can access on your computer. You can access it on your phone. If you were around a few minutes ago for Dr. Rachel Smith's presentation where she used open space, it's a little bit like that. You can go out into space and just go wherever you want and view whatever you want and do all kinds of cool stuff with it. It's a little bit like that. And it's fun for the whole family, whether you're an old nerdy scientist like me who was around when velociraptors were around, or you're a kid who would just enjoy watching me getting bitten by a velociraptor. Whatever you are, in there, Eyes on the Solar System is for you. There's a companion, Eyes on Exoplanets, which will show you all the thousands of alien planets that we found around hundreds of alien stars. And there's an Eyes on the Earth too. So there's 3 of them, but we're going to do mainly Eyes on the Solar System because we can focus in on Mars Perseverance rover. And in the meantime, an update on the screen back here. Remember, I told you we have radio dishes all the way around the Earth in Australia, Spain, and California to talk to the rover. And when we first started this program, we had to use the ones in Spain because we here in the United States weren't pointed at Mars, but Spain was. Well, they're switching over the dish now. We're talking in, we are also talking to the rover now in Goldstone in California, about halfway between Los Angeles and Las Vegas. You can see the Goldstone dish, Mars Perseverance robot. It's 203 million kilometers. 203, I thought they were mixing units. 203 million kilometers away from us. But we're talking to it from Los Angeles now. So we can go ahead and start our presentation with myself and Doug Lively with NASA-JPL's Eyes on the Solar System. You can go out and get that, eyes.jpl.gov, and connect to our big server in Pasadena and do everything that we're going to show you here in the next few minutes.
Hi, my name is Doug Lively, and I'm an astronomical league coordinator with the Raleigh Astronomy Club and a NASA-JPL Solar System ambassador. I've been in astronomy for over 22 years, and I'm looking forward to giving this presentation today.
Hi, I'm Ellen Rich, also a solar system ambassador with NASA's Jet Propulsion Laboratory, and sometimes tester for NASA software. What we're going to show you today is Eyes on the Solar System. It's one of 3. We've got Eyes on Solar System, Eyes on Exoplanets, and Eyes on the Earth. This is really cool, super cool. It's sort of like a Google Earth of space. You can go with this program, put yourself in space wherever you want to go in our solar system. Almost everything is there: planets, moons, spacecraft, comets, asteroids. Even Elon Musk's Tesla is on here. You can go to wherever you want. It's all live. And when you go there, for instance, you can actually virtually sit in an Elon's Tesla and then look at space as it would appear if you were sitting there. You can put yourself in Earth orbit. You can put yourself on a moon of Jupiter. Everything is in real time. And when you're there, when you do this at home, and that's one of the things about what we're going to do and give you today, is that we're going to show you how to do this at home. You can connect to a server at JPL, and it's eyes.nasa.gov. Doug's going to put that URL up, and I'm going to blab it a few times myself. But you go there and you can connect to this, and you can go explore space in real time. As I said, when you go out into space and go to these different locations, wherever you want to go, spacecraft, moons, planets, whatever, they are in that place. It's real time. You are where they are and seeing what you would see if you were actually on them. You can, if we have an asteroid fly by the Earth, you can put yourself on that asteroid and watch and see what the Earth would look like underneath you as real time as the asteroid is flying by. So many things you can do with this. It's real time. You're moving at the same speed that the object you're sitting on would be moving, and everything is in exact scale for size and distance and time, which means you go into space and that's what it looks like if you were really there. It's a really cool program. That's Eyes on the Solar System. Eyes on Exoplanets will take you to alien stars and the alien planets that we found orbiting alien stars. And you can go there. It's all artists because we don't have any real photographs of these, but the Eyes on Exoplanets is thousands of artist renditions and information about alien stars and the alien planets that we found. And the third one, Eyes on the Earth, is pretty much the stuff in Earth orbit. You can put your camera in Earth orbit right above wherever you live and look up into the sky, and that's what's there. If you see something go by you think might be a spacecraft or an asteroid or something, you can just look up from this program and say, ah, there it is. That's the International Space Station or whatever. So we've got 3 of them, but we're going to spotlight eyes on the solar system today because we're in the solar system talking about Mars and our new robot going to Mars. So we're going to kind of focus on that. And you can see on the screen behind me, this is the home screen for eyes on the solar system. You just take your cursor, and this is our solar system with all the, you can remove the orbit lines if you want. There's an asteroid, there's Uranus. It's all there. Zoom in close, and here we go to the sun and all this other stuff. Doug's going to show you. Doug's going to run you through this and show you how it works.
Thanks, Alan. And as Alan mentioned, this is NASA Eyes, Eyes on the Solar System. And it's a great tool from NASA. It's free. You can connect to it anytime. And you can, if you'll look at the URL I have right here at the very bottom of the screen, this is actually where you go to access it. Now, you will need to download it to your PC, and you will need an actual Windows PC, and you'll need an internet connection.
Oh, it works on Mac, Doug.
Okay, great. Thanks. So it's also for Mac as well.
Yeah,
so
for me, because I don't have a Windows computer.
Okay, so when you go to the URL, you'll see this top portion of the screen, and it'll basically you'll have a message that says download the app to get started. You click that button right there, and you can download the app. Now, when you actually get it on your computer, and you go to actually start it up, you'll, as Alan already mentioned, you're going to get 3 programs in one, and a lot more. But there's Eyes on the Earth, Eyes on Exoplanets, as Alan's already explained, and then a lot of really cool simulations for some tours, solar eclipses, the Juno mission. And there's a lot of simulations on this, including the entry, descent, and landing for Mars 2020 that Alan's going to speak to in a few minutes. But today we really want to focus on really how to use Eyes on the Solar System, and on the on how you can actually yourself at your own leisurely pace go out and explore the solar system. Now, when you start it up, you will get 2 options to either choose a simple interface or advanced. But today don't let the word advanced set you back, because that word actually means you're just going to get a lot more tools on your screen, and it's really easy to use. So we're going to look at that in just a second. I do want to just kind of give you an idea of kind of some of the things we'll talk about today. We will go to the moon. We will go to the Tesla that Alan talked about, and we'll look at where it's at actually in its orbit real time. We're going to look at the Voyager spacecraft, which is actually past our solar system. It's actually out in interstellar space now. And then we'll just kind of hop over to Saturn, Jupiter, and then finally Mars, where Alan will talk about the Mars 2020 EDL and Perseverance landing. Okay, so what I'm going to do is I'm going to stop this slide now.
Oh, hey Doug, let me mention one thing here. There's when you load this program, it gives you a chance to do some tutorials, and they're quick. It doesn't take more than 10 or 15 minutes to do them all, and it really helps you get started with being fluent at how to maneuver around in this thing.
So just like Alan said, over here in the right-hand corner, you'll see that there's actually a control here that says Tours and Features. And if you just click this button, you'll see that there's tons of tours here that you can take, and you can follow spacecraft as they head towards their planets. There's a lot of great tutorials in here, and a lot of great pictures to look at. All these are actual photographs that have been taken by the spacecraft, and they actually follow the actual orbits and the actual trajectories that were laid out by NASA navigators. So it's a really cool thing to look at. Just real briefly though, if we talk about our UI down here, you'll see this is really where our main control occurs. We have a destination box, we have a date and time control, we have your speed and rate, and we have visual controls. And we'll talk about each one of these in just as we go on. So in destination, right before I go on into that, as Alan kind of demonstrated earlier, you can just by clicking your mouse button, you can kind of grab the solar system and move it around. So if you want to see the solar system in its flat plane, you can do that. You can zoom it in and zoom it out. So on this visual control here, there's a great little zoom tool. You just click here and you can kind of move it up, and that will zoom us in towards the sun. Or if you want to go all the way out, you can zoom all the way back out to the outer edges of the solar system, as you can see we just did. You know, and if you kind of get things all messed up and discombobulated, you don't know where you're at, all you have to do is come over here to this little box right here. It's got a little picture of a house. That's your home screen. Just click that and you're back to where you began. So you can't mess things up. It's really super simple to use. And again, if you get confused visually, just hit that home key. So let's talk about the destination box just for a little bit. So the destination really is your control. This is where you can choose to go anywhere you want in our solar system. So you can see here that we have some ideas, the planets. We have dwarf planets if you want to cruise out to some dwarf planets. If you want to go to the asteroids, you can do that. Comets, and then spacecraft. So we can look at any of the spacecraft that NASA has launched. We can go look at them where they're at currently in their orbits and trajectories. So for now, we're just going to do a real quick, we're going to hit something. We're going to go to Earth's closest neighbor. That's the moon. And so we will choose Earth and then the moon. And then once I click moon here, we're going to get a little go tab. There we go. And so you see we're zooming in towards the moon. And you look, that moon looks kind of dark. It's hard for me to see anything there. Well, you're right, because the moon is at a phase where it's mostly dark when it's facing Earth. So if you want to see more of the moon, you can come down here. If you look right here on this right tab here, there's a nice little tool right here that allows us to illuminate things. And so we can fully illuminate the moon now and look at the moon. Again, these are actual photos of the moon that have been taken by NASA spacecraft. They've been stitched together. They're all high resolution photographs. And so that's one way that you can kind of control what you're looking at. I do want to point out right here, the bottom of, let's see here, bottom of the moon. This is the south pole of the moon. This area is known as Aitken Basin. And this is where the Artemis mission is going to be going. It's the southern pole of the moon. You can see that these craters here are still black, even though it's illuminated by the artificial light on NASA eyes. This is because these craters remain in shadow forever. So whenever NASA spacecraft went over and took pictures of the moon, there was never a time that they were lit. And that's a really great thing because we think there's a lot of water there. And with water and a lot of H3 that's thought to be in the ground there, that's a great place where you can actually develop a habitable place for astronauts for a future base. So this is the place where the Artemis mission is going, and we're going to be looking forward to that. And so again, you can always go out and explore this anytime you wish through NASA eyes.
Hey, excuse me, Doug.
Yeah, go right ahead.
Point out too, when you're rotating this around, you notice in the background sometimes there's the rest of the solar system is still there, and you can. I noticed in one of your screens it said Mars 2020, which is our Perseverance robot that's on its way to Mars, was like right behind the moon. So as you rotate around, you can see, the rest of the solar system in the background, and you can click on any of those things. If you're looking at the moon like Doug's doing right now, and there was Voyager 1, which is outside the solar system. But if whatever you see behind whatever you're looking at, if you want to go there, you just click on it, and you immediately, at many times the speed of light, fly there. And that's what Doug did. He just went 17 and a half light hours
miles. Yeah, 17 and a half light hours out to Voyager 1, and that was really one of the spacecraft that we were going to visit today. And I think it's a great segue just to kind of show you. I'm going to lighten it up here with the illuminator, and you can see the spacecraft. And I am now using my mouse to kind of position the spacecraft to where it's actually looking back towards our solar system. It's gone beyond the actual edges of our solar system as in interstellar space. And this is a great example of how great this program is. Because again, you can just do what if scenarios. Hey, I want to look at Voyager. I want to look at where it's at. or I want to look at some other terrestrial or near terrestrial object. So it's a really great tool for using. Let me just go back. I'm going to go back a little bit towards Earth. A few minutes ago, Alan mentioned another spacecraft. And so, for instance, you saw that I was actually able to click on the name of Voyager. But if you don't remember the name, say which one it was, Voyager 1, Voyager 2, you can always come down here to spacecraft. And if you click spacecraft, you can see all the spacecraft that have gone to objects. So in this case, this would have been Voyager 1 would have been in the outer planets list. We can go to, there's also some other missions, which is pretty cool. And so these are missions that don't necessarily, aren't necessarily categorizable. And one of the ones is the SpaceX Starman Roadster. So we're going to click that, and another 17 light hours into the solar system. We're going to zoom right in.
We're violating the principles of physics here by going faster than the speed of light.
All right. And here you go. You can see that we have the Starman right here. We can zoom right in on that Roadster, and sure enough, there's the light, or the dashboard is saying, "Don't panic." So so we are actually seeing the Starman Roadster in its actual orbit, where it's actually at space at this very moment in time. Do you want to say anything else about that, Alan?
Well, again, you can like configure this with your mouse so that you've got kind of a view of if you're in the passenger seat, and rotate it around and see what the see what anything in space, whatever is close by and whatever you can see. It just, wow, you see it.
Sorry about that.
And the other thing you can do with this too is, I don't know if you're going to, I hope I don't steal your thunder here, but
go ahead.
In the bottom, your speed and rate, as I mentioned before, everything here is moving real-time speed, but in space, you can't really, feel speed that much. For instance, if you go to Saturn or Jupiter, a planet that's got lots of moons, and you see all the moons there, and in real time, they don't look like they're moving at all. But if you want to see the orbits of the moons of Saturn or Jupiter, you go down to this third bar from the left down at the bottom, your speed rate, and you crank that up to artificially fast. And then you can just watch they're just buzzing around like crazy, like bees going around a jar of honey. If you want to visualize the orbits and all these moons of someplace like Jupiter or Saturn. And the other cool thing to mention is Doug was on Voyager spacecraft a few minutes ago. We have a 3D mode in this. It's on the toolbar over to the far right. It's the old-fashioned 3D mode that you have to have the glasses with the one blue and one red lens. If you got a pair of those, you can go to 3D mode. And it's not really that interesting for most things, but Saturn's rings and a spacecraft that's a long spacecraft that has a big boom arm, and that you can move around and look at in 3D. Yeah, those, you have that, you can just move the sets with your mouse, your cursor, you can move Saturn's rings just where they look like they're about to slice you off in the neck, and it's pretty cool. But otherwise, 3D mode is not. There you go. You can imagine what this would look like in 3D if you were doing that, moving the edge of the wings, the rings.
Yeah, it's quite cool. So I don't have my 3D glasses with me today, but yeah, it's really cool. And that's, I think while we're here on Saturn, I think it's really interesting to note, again, if there's something interesting about Saturn, like if you click, if you do one of the tours and one of the Saturn tours with Cassini and everything, you can actually click up here on this polar region. I think it's actually, you can get information over here on the side. We just hit I, and then you can also get current location, other current location data as well. And then, right. And then I think that so that was both Jupiter and Saturn that we visited. And as Alan said, you can again use this. I'm going to go back to the solar system, so I'm just going to go back to our home situation. And let's say you just wanted to if you wanted to see the solar system at any date and time, that's another really interesting one. So if we go back to 1977 and September 5th, does anybody remember what date that was? That was actually the date that Voyager launched. And this is what the solar system looked like on the day of that launch. And you see, we don't see Voyager out here because it hadn't launched yet. So that's another really cool thing about this program is it keeps relevant date with respect to the mission data. So anyway, just to know that, and it's a other neat thing to do is you just put your birthday in there. You can see what the solar system looked like in your birthday. As Alan also mentioned, you can use the speed bar right here to speed the solar system up and just watch the solar system. Now you see Voyager and Voyager 2 and 1 launched, and you can see their trajectory as they're heading out towards the outer solar system, and the different ways that they actually change their trajectory based on gravitational pull of planets, which I think is another really cool action. So that's another neat thing to do. Again, your speed, you can set your speed also, again, with this slider bar here, or you can also set it to a pre-selected speed by doing this pop-up box here. So I'm going to close both those. I'm going to go back to now, and I'm going to go to real time. And again, I'm going to go back to home. Okay. And now we're going to choose a new destination, and that will be Mars. And actually what I want to do is I want to choose Mars spacecraft. So we're going to take spacecraft, go into Mars, and we're going to select Mars 2020, which is the big event. So I'm going to go there, and this is now in late February. This is where it is on February 15th, but for the EDL, we're going to choose that time. And we should be able to zoom around here and see how close it is to the red planet. All right, so that's really kind of my tour of the tools of for Mars Eyes. I just really invite you guys to take the tool, download it, spend some time learning how to use it, and you're going to have a lot of fun just tooling around the solar system. And I do invite you, as Alan mentioned, to try the exoplanets and the survey of Earth that's on the in the main menu. Those are really great programs. So I'm gonna give it over to Alan now as he talks to us about Mars 2020 and the landing of Perseverance. Alan?
Okay. A couple other things to mention that you can do. You can do so much with this. For instance, if you ever wondered, like from watching Star Trek, when they're sitting in their conferences and the stars are flying by, and you go, how fast would you have to go into the stars fly by like that? And you can actually point your virtual camera and eyes at the center of the Milky Way, and then use that little speed device down there that Doug was just using, and just crank it up, crank it up, crank it up to go exceed the speed of light. Just keep going, and the stars never seem like they're gonna move, but eventually they start to move. And I think you're going like some really stupid number, like 22,000 times the speed of light when the stars start to move past your window. So, and this is all real stuff. It's all real scale and real time. So that's your answer. How fast would you have to go if you wanted to see stars move by your conference room windows in the Starship Enterprise? And this this screen that Doug has here, I'm supposed to be talking about Mars 2020. What I did for the last, what I did for the last robot, Curiosity, I set this. I put my camera on the shoulder of Curiosity as it was on its way to Mars, and just left it like this. And that was my screensaver. So that in the beginning, like 3 weeks before it actually got there, you could see the little red dot. And every day I looked at it, the red dot would be getting a little bit bigger, a little bit bigger, a little bit bigger. And then on the day of entry, descent, and landing, there's Mars that is just huge, looming in front of you. But you can, and it's all real time. So it was just as if I was on board Curiosity on the way to Mars, and that's what Mars looks like, and getting a little bit bigger every day. So many things you can do.
If you guys are really kind of curious as to how big this is with relation to things that we all know really well on Earth, you can just click right here, and we've got some tools. Actually, where's the tools here? It's
I saw that measure distance from. You can click on any two objects like Earth and Mars 2020
right.
robot, and it'll tell you how far they are away from each other and how fast they're moving in relation to each other.
Right.
What Doug was showing you a little while earlier with that speed, rate, and time thing, the default, it brings you up to right now when you go into space. But for instance, there have been events that have happened in the past or if you're on Perseverance going to Mars, you can change that to 2 weeks ago and see what Mars looked like from Perseverance 2 weeks ago. Or you can change, if you knew there was an asteroid that flew past the Earth on January 4th, 1987, you can change your date to that and go there and ride that asteroid as it flew past the Earth. So you can change the date. I think it's, what is it? Any 200 years in the past or 200 years in the future, something like that. Anything that's happened that NASA has in its database. If you want to know where Jupiter was last week at 2 o'clock in the afternoon on Tuesday, just change it.
Right.
That'll show you where Jupiter was. Right behind me, guys, is Eyes on the Exoplanets. And you get some sheets that come up with that too. We've had a few missions that, and here is TRAPPIST-1, this system that has lots of planets in it that have been found, I think, by the Kepler Space Telescope. And you can go to, and these are all artist renditions. This is the whole system with all these planets. And you can see, you can click on the star, the alien star that's in the middle, and you can get information about that star. You can get the system here. And notice how the center of the system is green. That's the habitable zone. We sometimes call that the Goldilocks zone, where it's a planet, if it's there, it's in an area that's not too cold and not too hot. So this might be a good place for life to be found on these planets. You can click on the individual planets and it brings up the artist rendition of that planet based on what the scientists think the planet looks like in real life. And that one was kind of like Earth. So Eyes on the Solar System, it tells how far away it is, 41 light years from Earth, and you can click on some of these other things and get more information about this alien star and this alien solar system. And there's hundreds of them there. There was mostly from the Kepler mission. Yes, the Kepler Space Telescope. Okay, this is the module on Eyes that you can get from, you can Google Perseverance Landing Event, JPL, or a couple of different ways. We might have a URL for you here. But this is close to what's happening in a couple of days. It's got different stages of the landing. This first one that comes up is the cruise balance masses ejected. It tells you you're like over 1,000 miles from the landing site. The altitude above Mars is 350 miles and dropping as we watch it. The velocity is almost 12,000 miles an hour, and it's 9 minutes away from touchdown. So it hasn't quite entered the 7 minutes of terror yet. It'll do that in a couple of minutes. And you can just let this play real time, or you can swipe it up on the bottom left, scroll for the next phase, and it will take you entry interface point. When well, there we go. We went all the way there to surface operations, but that's cool. You can take it all the way to the ground. But this, the cool thing that we're talking about for entry, descent, landing is this procedure where Perseverance arrives at Mars at 12,000 miles an hour. It first has to do aerobraking, come in like a meteor or like a Soyuz capsule, or the way we used to do shuttles and Mercury, Gemini, and Apollo, and you see the heat coming out. It slows down quite a bit there. And the second phase is hypersonic parachutes come out to slow it down even further. And those are parachutes not like anything on Earth, because this is very thin atmosphere and they're coming in hypersonic. You can't even test that on Earth. Then when the parachutes release, we go into this sky crane maneuver where there's a powered descent, where the a robotic rocket actually flies the Perseverance robot around and looks for an ideal place to drop it, and then it deploys the Perseverance robot on bungee cords. There's the rocket, and that the Perseverance robot is up underneath it right now. And as it gets close to the ground, this artificial intelligence rocket-powered robot taxi cab lowers the Perseverance robot by bungee cords close to the ground. And it's no humans are helping this. It has to be, it's the signal speed is so far away that this thing has to, there it goes. It's deploying the robot on bungee cords. And this all has to be done. It has to find a good place to land where there aren't boulders. And it has to, precise timing. It's smart. It has to do this without the help of humans. And when it sets the robot down, it detaches the bungee cord with explosive bolts, and the spooky looking rocket powered smart Mars taxi flies away and crashes someplace. Its job is done, and Curiosity is on the ground. Same thing we did. Oops, I said Curiosity. This is Perseverance. This is the same way we landed Curiosity, the smaller brother of Perseverance from years ago. So it's the second time we've done it this way.
You can actually see the heat shield over in the far field away from Perseverance, and then supposedly this is where the back shell is. Mm-hmm. And we should see the sled over here. Oh, here's where Earth. Let's see.
That's where Earth would be. Yeah, it's behind that hill.
Not really sure that they've got where the sled is. There, heat shield. So we don't know where that's going to go. All right, that's all I had. All right, goodbye, everybody. Hope you enjoyed the program, and I look forward to seeing you out at future NASA Solar System Ambassador events.
Thanks for watching us, guys, and hang on. The actual EDL and landing will be coming up soon. Don't go anywhere. Stay tuned. Hi, everybody. I'm Alan Rich.
Well, welcome back, everybody. I hope everybody takes a moment at some point in the very near future to go and check out the Eyes on the Solar System platform. I know that anytime I've got a little bit of downtime and I'm thinking about space, got space on my mind, the Eyes platform is so much fun to just explore, but also learn something new about the space that we inhabit. Alan, thanks so much for bringing us that presentation.
You're welcome. That's fun. It keeps me up late at night sometimes.
just soaring all over the place, all over the solar system.
Yeah, yeah.
And so I went and I got a little bit of Mars to bring back with me while that was going on. It looks like you quite the fashion icon there today.
Yeah, I'm changing clothes regularly. And in fact, as soon as we start the next presentation, I'll have a different ensemble on, and I will have brushed my teeth and flossed. And you guys are noticing that. It only takes me like 10 seconds to change clothes and brush my teeth, comb my hair, floss.
It's Mars landing traditions, right?
No, not really. That's just peanuts. And making peanuts, guys. Remember to eat your dry roasted peanuts. We are down to about 2 hours before landing, and anxiety and nervousness is kicking in, and that's what dry roasted peanuts are for, a JPL tradition. I have a handful of them right now. And if you notice behind me, we are setting up to, whoa, we're already connected. We've got, remember earlier this morning, we were talking to the robot by radio dishes in Madrid, Spain, and now the Earth has rotated around, and the United States is coming into view from Mars, and we've got one of the two dishes in Goldstone in California that is now talking to Perseverance, which is again going at over 12,000 miles an hour. And what Perseverance is saying to us is like, no, stop. Mars is just coming up at 12,000 something miles an hour right in front of, that's got to be freaky. I'm glad I'm not on that. But anyway, this next presentation, Ken Brandt, a solar system ambassador from North Carolina, and also with the Robeson Planetarium, is he and I are going to talk about the Perseverance rover itself, to tell you all you want to know about it, all the bits and pieces, how it works, how it was made, just anything you want to know. That's coming up next.
This is Sean Bale, the Solar System Ambassador for NASA-JPL, coming to you from somewhere in North Raleigh, North Carolina.
And this is Ken Brandt, also a JPL Solar System Ambassador and the Director of the Robeson Planetarium, coming to you from Lumberton, North Carolina.
And hi, my name is Mike Keefe, also a Solar System Ambassador, and I'm coming to you from Apex, North Carolina.
For hundreds of years, we've been exploring Mars. Of course, most of that exploration has been very remote with telescopes from here on Earth. But in the last 61 years, we started actually sending robots to Mars. And this presentation will go through that story of the 47 missions that have successfully made it to Mars, or not successfully in many cases.
One thing that we've known from Mars is that Mars is hard. It has the combination of a variety of factors, which include only being aligned for missions approximately every year and a half. It has an atmosphere that's definitely present, but not significant enough to provide conditions like Earth, but it certainly makes it difficult to land. And as we've explored, the early missions, as you can see here in the 1960s, were started with flyby missions, where we were dealing with just getting to Mars and getting to a range that the cameras could take pictures and do scientific studies from space. We, of course, moved on from there to a fleet of orbiters, the first of which, of course, was Mariner 9. And Mariner 9 took some amazing pictures in its time in orbit. Today, we have 4 major craft in orbit, probably the most decorated of the bunch being the Mars Reconnaissance Orbiter, which also satisfies the opportunity to send data from the surface of Mars back to Earth as a relay station. Of course, then we move on to the surface, where it gets very difficult. And at that point, we see the orbiters are doing surface detail to give us landing sites and understanding of the terrain that we might be landing in. You can see how the technology has progressed in this image, where from the early days of Mariner 4, we were dealing with amazing resolution pictures from our HD world that were approximately 200 by 200 pixels. Moving into Mariner 9, we actually increased the resolution to an amazing 945 by 704. And then, of course, you can see more recent images from MRO, which combines a variety of cameras in multispectral pictures, as well as multiple CCD elements per resolution and spectrum. That gives us a maximum resolution, believe it or not, of some 100,000 by 40,000 pixels. Once you get to the surface, however, you start with the landers. Back in 1975, Viking was the first successful landing by NASA, followed in the early 2000s with the Phoenix polar lander, which was actually looking to dig up some water ice and, of course, achieve that objective. But, of course, being in one place isn't really good enough. So we built rovers. And you can see the family portrait of rovers here, ranging from the initial test bed of Pathfinder, the small guy in the middle, to the mama robots being Spirit and Opportunity. And lastly, we get to the big boys. The Curiosity is pictured here, as well as what we're about to be witnessing in a day or so, the Perseverance lander. So to take you through the timeline in more detail, I'll turn it over to you, Mike.
Thank you very much. So we did talk about that we've been exploring Mars robotically for quite some time. And in 1960 and 62, the Soviet Union sent 4 flyby missions and 1 lander mission. Unfortunately, they all failed to achieve their missions. In 1964, the U.S. sent its first flyby mission, Mariner 3, and that unfortunately was not a success either. However, we also sent Mariner 4, and that one was a success. And Sean mentioned the resolution of one of the first pictures. So Mariner 4 was the first human spacecraft to do a successful flyby past Mars. The Soviet Union again tried with Zond 2 as a flyby, and that was not successful. NASA continued with success with the Mariner 6 probe, or the Mariner 6 flyby. Again, a few other unsuccessful missions for the Soviet Union, another flyby for us, Mariner 7, and again, not so successful orbiter for the Soviet Union. In 71, we sent our first orbiter, Mariner 8, and that was not a success, unfortunately. Followed up by some other Soviet missions. And then we get to the Mars missions that the Soviets put forth. And we have to talk about them all in context with Mariner 9. Now, even though Mariner 9 launched after those Soviet missions, Mariner 9 was the first to successfully enter Mars' orbit. It arrived 13 days before Mars 2. So technically, it was the first to enter Mars' orbit. Mars 2 did enter. It had a lander component. Unfortunately, the lander crash landed, so you can't call that one a success. Mars 3, they made a soft landing, and I believe that they had about 100 and some odd seconds of, so I guess that was the first successful landing of any Earth spacecraft. And then we had a few more missions from the Soviets, Mars 5 being one of their successful orbiters. And unfortunately,
Mike,
Mars 6. Yes.
Can I throw in a quick word about Mariner 9?
Yes, of course.
The neatest parts about that mission and why it succeeded where the Russian missions didn't do so well is because when it arrived, the JPL realized they were in the middle of a major dust storm. So the surface was obscured. And so they put Mariner 9 into sleep mode. They said, just park in orbit for a couple of months. We'll wake you up eventually. And so Mariner 9 was able to get thousands of successful images from the surface of Mars that Mars 2 and 3 didn't see because they were looking at dust. So this is a point that we built into the software of the robot, the ability to sleep and wake when needed, just in case something like this came up. Thank you.
Fantastic point. So we leave 73 with another a flyby and a lander from the Soviets. The flyby was successful, the lander was not. And then we jump to 1975, and that was the Viking missions. So Viking 2 was the second lander, but the first US successful lander. And it operated for 2,245 sols, which is the term for a Martian day. Viking 2 operated for over 1,200 sols. So you can start to see when we compare the landers, about 104 seconds on the first one ever, and then we've got years and years and years. This is over 6 years that Viking 2 operated from the surface of Mars. And then the red planet went quiet all of a sudden. Didn't really do much as Earthlings to send more missions. We had another failed mission from the Soviet Union. Phobos 2 had an orbiter, a lander, and a rover. The orbiter was successful, however, the lander and rover were not. And then it took until 1992 for us to send the next mission. And I should point that the year timelines above are launch dates, not necessarily when we landed. That's when we were launched from Earth. So 1992, the Mars orbiter unfortunately failed. If memory serves, this was the result of a units confusion between, I believe, metric and US or SAE standards. But then we sent Mars Global Surveyor, an orbiter, in 1996. That year also saw now the new Russian Federation send its first orbiter, lander, and penetrator. Unfortunately, that did not make it there. And we jumped to Mars Pathfinder. So the Mars Pathfinder Sojourner, that was the first rover to ever operate on another planet. And Mars Pathfinder launched in December of 96, but it landed on July 4th, 1997. It was a proof of concept that NASA was looking to make sure we can do low-cost spacecraft with frequent launches. And the mantra was cheaper, faster, better. And if you look at Mars Pathfinder, it was 12 and a half times cheaper than the Viking missions. And its goal above and beyond being a proof of concept was to return geological, soil, magnetic property, and atmospheric data. And you can see some of the components. The Pathfinder, or the lander, was subsequently named the Carl Sagan Memorial Station. And then the little robot rover was called Sojourner. So now we have an animation of the actual landing. You'll notice that we're deploying airbags here. Very happy people. We see Sojourner deploying there. And I remember this very, very clearly because this was the first time that we witnessed these near live updates of pictures on the internet. And I just remember sitting at work and just downloading and refreshing the website, several times a day just to keep up on where things were. The planned mission was only for 1 month for the lander and 1 week for the rover, but the whole mission actually lasted 3 months. And again, harken back to our comment about Viking, and you'll hear this theme continuously repeated with some of our Mars missions. It is interesting, Sojourner only traveled a total of 300 feet, 330 feet during its entire mission, and it never ventured further than 40 feet away from the lander. The lander sent back over 16,000 images, and 550 were sent back from the rover. And again, as I mentioned, this was just leveraging the new technology of the internet and having these things almost posted instantly on the websites. One of my favorite memories is just seeing all of these rocks that they named after cartoon characters. You can see there's a panorama up top of all the different things that they named. But Yogi was, I think, was the first one that I remember. Even Pop-Tart. But the key findings, in and above and beyond being this, proof of concept and just showing off the technology, they found that the rounded pebbles and rocks that they found near the land site really suggested that they were formed in running water during a warmer past where liquid water was stable on the surface of Mars. Also, that airborne dust is magnetic, and that an active water cycle in the past probably had leached out these, this iron from materials in the crust.
And Mike, one of the other interesting aspects of deploying a rover, we learned quite well with little Sojourner. We're dealing with a pretty significant time delay for radio communications back to Earth, anywhere between 4 and 13 minutes. So if you're roving around on the surface and you encounter an obstacle, say, for example, a rock the size of Yogi, there's not enough time to actually send a command to stop. So it gave us the testbed opportunity to see what it's like to drive around without being actually live controlling the rover. And there were some really funny pictures of bumping into rocks and getting the wheels all out of alignment on top of a rock. They were really quite humorous to see in the day, but it was really a science and engineering experiment to prepare for the larger craft later.
And I love that picture that you had of the rovers. That, I mean, it really was that you can see the generation and generational kind of impact each one of them had. One begat the other. It was really impressive. I wish I had been there to take that take that photograph of the three.
And when you think of how we actually were landing these craft, you've got the initial landers, which were primarily retro rocket landed. When you get into something of a much smaller, lighter weight, like Pathfinder, that's how the airbags would be successful, up to about the size of Spirit and Opportunity. But when you get to the size of a Curiosity or a Perseverance, now you're dealing with a much heavier craft where the weight of the airbags would actually be higher than the weight of the spacecraft, of the lander. So that technique doesn't work anymore, which leads to a pretty exciting technique I think we're going to be talking about later.
Absolutely. And just to note, you can see the kind of the deflated airbags around this panoramic view. So that was the Pathfinder mission. In '98, Japan sent its first orbiter. Unfortunately, that did not meet with success. And again, Mars is hard, as you put it. We did send the Mars Climate Orbiter, again an orbiter, that did not meet with success either. Neither did the Mars Polar Lander and Deep Space Impactor. So this was a lander and a penetrator. But then we start to hit our stride, I think, as explorers. So we had the Mars Odyssey rover that you mentioned. We had the Mars Express, that was an orbiter and lander. The orbiter was successful. And then we had the amazing twin rovers, Spirit and Opportunity. So with that, Ken, I'm going to hand it over to you to talk about Opportunity.
All right, so I'm going to specify Spirit did a wonderful job and lasted for 8 years on Mars and eventually got stuck in a sand dune in the Columbia Hills after having found lots of evidence for hot springs up in the hills. And actually, Spirit's landing site and Spirit's traverse site was actually one of the final 4 destinations for Perseverance. When they were doing landing site selection, one of the landing sites in the final 4 was the Columbia Hills. And that came pretty close to actually getting selected for a return visit because what Spirit found was so interesting. But Opportunity is my favorite of all the Mars missions. And the short version is longevity. First off, it landed right in front of a rock outcrop. Now, to somebody who studies geology, which is what a lot of the Mars scientists were trying to get at, is the geology of the water on Mars. It landed in a perfect place. It landed in a crater that wasn't too deep for it to drive out of, and yet it was shallow enough to expose this bedrock outcrop in front of it, about 3 feet tall. So rather skinny outcrop, as outcrops go, but it was filled with layered sedimentary rocks and these concretions called blueberries, which were hematite nodules that had formed in the presence of liquid water. So here was the evidence for liquid water on the surface of Mars right in front of them. They couldn't have planned it better. Let's put it that way. Now, Opportunity lasts for over 5,000 sols on Mars. That equates to you living to be about 5,200 years old. Okay, it drove over 28 miles before it was done, and this is an example of the terrain it was driving on. Yeah, look at that pretty smooth gravelly surface. I mean, pretty ideal conditions. If you have to do off-road driving, this is not a bad place to do it. You just got to watch out for the occasional crater and sand dune along the way, but you could do a lot of driving. And there was fortunately, there were lots of impact craters to be explored, because what an impact does for you, it exposes the bedrock underneath the surface. And so those impacts are great for getting down into the past and looking at the layers in the sides of the crater rim. And Opportunity did that with several craters, including the last one it was in, called Endurance. And Endurance crater is a huge crater. It's very large. I don't know the exact dimensions of it, but I guess if we could go on to the next one, Mike. But you can see part of the rim of the crater here, Lewis and Clark Gap, Marathon Valley. And Opportunity's location ended up being the rim of Perseverance Cove, appropriately enough. And that's when the dust storm hit. Go forward, I guess. So you can see the traverse, the 28 miles, just over 28 miles, and over 5,100 sols or days on Mars, 14 and a half years for us here on Earth. It starts out at Eagle Crater and traverses across the plains here, making a stop at a crater or two. It had to go sideways because there's a dune field out here in the middle that it had to kind of dogleg around, and then made it to Endeavour Crater. And Endeavour Crater is where it ended up stopping. And if we go forward, now that's a selfie. Now you've gotten pretty used to with rovers these days. Rovers extend their robot arm out in front of them, turn the camera around, and shoot back towards the rover. And what you get is a picture of the rover itself. And you can actually learn a lot from looking back at your machine. For example, looking at Curiosity's wheels, you can see the wear and tear on the wheels caused by the interaction with Martian rock. But here, mostly what you learn from this is solar panels getting covered up with dust. And that's sort of foreshadowing. So in June, I think it was June of 2018, a major dust storm envelops Mars. You can see this time lapse over about 2 weeks. Each of these panels here represents a shot looking at the sun, trying to measure an atmospheric quantity called tau, which is the interference of the atmosphere to the sun. So you see the sun's really bright, overwhelms the image here, kind of bright, a little dimmer now. It's showing up as a point of light, and eventually you can hardly see it. So you can imagine the power drain on solar panels, trying to gather power from the sun. You can hardly see it in the sky because of the dust. And then that ends up killing the rover. So this is Opportunity's last whoops, okay. That was, we'll get there in a sec. But Opportunity's last panorama is looking down into Perseverance Cove in the rim of Endeavour. And you can see still more layered sedimentary rocks. And these would have been great to explore in greater detail, but Opportunity never got that chance. And of course, her last signal could have been, my battery is low and it's getting dark. So that may be what Opportunity was communicating to JPL as the lights were going out, as the power was going out. So,
and you know, Ken, you said earlier that your favorite was because it had such a longevity with Opportunity. Mm-hmm. There are a couple of ways to make these missions very cost effective. One is to build a very cost effective piece of machinery, and as you mentioned earlier, Mike, the thought of faster, better, cheaper. But the other way to do it is what these craft have proven, that these were intended to last on Mars for 90 days. Mm-hmm. And we're talking about craft that did science for years. In Opportunity's case, what, about 8 years, right, Ken?
14 and a half, yeah.
So you can think of how many 90-day increments are in 8 years, and that's the equivalent of how many design life rovers we'd have to send. So we really got our money's worth in a tremendous amount of science.
Yeah. And NASA's rule is, the mission was only supposed to last one Mars, they funded it for one Martian year. And at the end of every funding cycle, the Opportunity team would go before NASA headquarters and say, hey, we need more money to keep this mission going. And the rule of thumb has become at NASA, if the mission is still flying or is at its destination doing good science, we keep funding it. The example, of course, being Cassini going around Saturn, and Opportunity. So numerous examples of extending funding for a mission that's already in place doing work. Curiosity is another example of an extended mission.
And same thing with Mars Reconnaissance Orbiter. It is well past its estimated life and been renewed several times.
Getting a lot of money's worth. So we come back from the amazing twin rovers. We had our Mars Reconnaissance Orbiter, just showing a few slides again of those. We had the Phoenix lander in 2007. Again, as Ken mentioned, this lander found water ice on the surface of Mars in its polar.
It also has found snow. Mm-hmm. It actually snowed off in the distance while I was looking at the clouds. They actually saw snow flurries.
Yep.
So the snow's up.
Which ultimately killed the craft, because that snow started building up on the solar panels until it got so heavy the solar panels actually collapsed from the weight of the snow.
Yep.
Yeah, and you have to keep these things warm. If they don't stay warm through, in this case, solar radiation, the electronics will die inside. So.
And the other kind of fortuitous thing about the landing, when the retro rockets fired, as Phoenix was landing, it cleared away a lot of the regolith, the dusty sort of soil on the top, and lo and behold, some of the first pictures we got back of the lander's feet on the ground actually showed some white material, which caused quite a stir in the scientific community. It turned out it was indeed water ice.
Yeah, absolutely. So then in 2011, we have a joint Chinese and Russian mission, orbiter, and can't remember what I had the abbreviation for SR. But then we had MSL Curiosity launched in 2011, and we're going to have Ken take us through a little bit more of Curiosity.
First off, when Curiosity landed in August in 2012, it landed using that sky crane maneuver you're going to hear more about in about half an hour when we talk about entry, descent, and landing in some detail. So stay tuned for that. But basically, this thing gets lowered down on a set of wires attached to a rocket pack that drops it gently down on the surface. And then a whole bunch of what are called pyros fire, chopping the cables and sending the jetpack off to crash elsewhere on Mars, leaving our rover, our very dusty rover, I should point out in the selfie. This is probably, I think this was in 2019, so about a year and a half ago. This picture was taken, and you can see more of the same, the dust. And again, this is done. You can see the shadow of the robot arm here that's taking this picture. There's a camera on the end of the arm. It extends 8 feet out in front of the rover and then shoots back at this picture. Nuclear powered. So we've ditched the solar panels in favor of a plutonium power source that provides heat for a thermocouple to provide you electricity for the rover. And if you look carefully at this middle wheel here, you'll notice it's got some dings in it, got some holes and other things in it. And those holes are the result of interacting with the rough Martian rock. And for Perseverance, of course, NASA redesigned the wheels and hopefully have a more robust set of wheels for the rover coming down this afternoon.
And Ken, along those lines, we learn by doing, right? And we saw what happened to Spirit getting caught in a sand trap with fairly small wheels. So you can pretty clearly see from this image, Curiosity, it's dune buggy wheels to keep us from falling into the sand, right?
Yeah, bigger wheels, yep, definitely. But the basic dimensions for Curiosity and Perseverance are the same. Perseverance is a couple of hundred pounds heavier. It has more instruments on it, but other than that, it's basically the same body build as Curiosity. Go forward, please. So this is Curiosity looking out in its first month of landing on Mars. The circle up here, the ellipse up here, shows its approximate location today. So you can see how far it's traveled across the hills of this crater, Gale Crater, leading up to this mountain right here by the word Sol, Mount Sharp, which goes up about 5 kilometers? Something big. It's a pretty tall mountain. So these are the different layers Curiosity is traversing. Curiosity's gone through all these units here, and it's just getting into the border between the clay and the sulfate unit on Mount Sharp. And again, another lake bed. You're going to hear more. You've heard already about the lake bed that Perseverance is landing in. We have another lake bed here that Curiosity landed in, and all kinds of evidence for organic molecules. We've even been able to measure seasonal variations in methane gas in this area on Mars, and that's very intriguing because methane on Earth is normally formed by living processes, bacteria that produce methane as a waste gas in swamps, for example. But here, there could be a geological explanation as well. Water could be interacting with olivine, producing methane gas, as one example. But life is not out of the question here. You know, with Mars and the search for life, Curiosity has just made more clear the case for there's probably something that was alive on Mars and maybe alive now. We just haven't found the bodies yet. It's kind of like a murder investigation. We've got everything except the body. You know, we have everything except the body here. So, second. And you can see Curiosity's traverse here. They had to go around this patch of sand dunes here because they learned their lesson from Spirit and to a certain extent, Opportunity getting stuck in sand dunes. So they said, no, we're driving around that. So they drove around it and found a pass here, and they cut up into the mountain here. So this is as of about 100 sols, about 100 sols ago. This traverse map was done. And you can see the different units here. The different colors of the units which correspond to the geological map on the next page. These are the clays, clay and sulfate, hematite and sulfates, and you're going this way up the hill. So here's a river outflow channel here. So Curiosity is actually driving in this general direction, going towards from top left to bottom right. And I think that's it for Curiosity. Is that it?
Well, I want to comment there, Ken. When you look at that picture, you see that stream channel. This is visual evidence to confirm what we've seen on the surface, that all over Mars, you have clear evidence of erosion patterns from water or a liquid flowing. And from MRO photographs that we have, we've actually, based on seasonal variation, when the surface warms up a bit on the side of a crater or a hill, we've actually got pictures of what turns out to be flowing water on the surface because it's warmed up enough to go from the ice state to the liquid state, and it's all based on seasonality. So just to reiterate what you said earlier, Ken, there's an abundance of evidence of how much water was, and even to a small degree still is, on Mars.
As we're wrapping up this presentation, I want to point out one more thing, and that is the degree of the surface which we've actually explored up close. If you look behind me here, you see cinder blocks, okay, on the wall. And if I point out one of these little depressions in the cinder block, and that one block, if this entire wall is the surface of Mars, we've explored that one little dimple in detail. There is so much more we're getting ready to explore, and we need to explore to tell the whole story about Mars. But we know a heck of a lot more than we did 6 years ago. That's really to NASA's credit and the other space agencies that have been successful in launching all these exploratory vehicles. You know, we've gotten a picture for what Mars was like a long time ago, and to a certain extent what it's like today. You know,
absolutely. So we finish off our timeline here. We see that India sent a successful orbiter launched in 2013, the Mars Orbiter mission. We also launched from NASA the MAVEN orbiter. And in 2016, we had the ExoMars orbiter and lander with the EU and the Russian Federation. Fortunately, the lander was not successful. In 2018, we had the InSight lander. And now in 2020, here we are. We have got the EAU's Mars mission HOPE has arrived in Mars. We have China's Tianwen-1, an orbiter, lander, and rover. That has also arrived. Landers have not been deployed. And of course, we have, last summer, we launched Perseverance, which will have also Ingenuity, so our rover and helicopter. So that wraps up all 47 missions. Successful and not so successful.
Well, and the old adage up until recently was that Mars has a habit of eating spacecraft for lunch. Of those 47 odd missions, 27 of them have failed or partially failed. So Mars really is hard, but as you can see, we're getting better and better at this.
Practice makes perfect.
And I vote for more practice.
There we go. Well, I want to thank you, gentlemen. It's a great discussion on the history of Mars exploration, and thank you to the museum for hosting this.
Go Perseverance.
Yes.
Percy.
Well, welcome back, everybody, to our live virtual landing event to celebrate what we hope will be the successful landing of the Mars 2020 rover Perseverance. Sorry for the mix-up that we just had in the scheduling there. We got the history of Mars exploration switched up with Meet the Perseverance robot. So I want to thank the presenters on that one, Mike Keefe, Ken Brandt, and Sean Bale, for delivering that great summary of all of the robots that have gone to Mars to help us learn more about the red planet. Excellent job, guys. Learned a whole lot. But it kind of works out because now that we've learned about all the robots that have been to Mars, you're now ready to learn about the robot that is scheduled to land on Mars very soon, Perseverance.
Hi, everybody. I'm Alan Rich, Solar System Ambassador with NASA Jet Propulsion Laboratories. As you know, today, our newest robot, the big, smart Perseverance, formerly known as Mars 2020, is landing on Mars. And this presentation is about the robot itself. Meet the robot, meet Perseverance. Everything you always wanted to know about it that we can cram into 20 minutes or so. And with the presentation here, I'm going to turn it over to Ken Brandt. He is also a JPL Solar System Ambassador, and it looks like he's sitting in mission control at JPL in Pasadena, which is a cooler background than I've got. So Ken, introduce yourself and then start the show.
Very well. Good afternoon, everyone, and welcome to the landing of Mars Perseverance. Woo! We've been looking forward to this day for a while, and I'm hoping you have too. We're going to try and bring you up to speed on what the rover is, what it's got aboard, and what it's going to try and do. So I'm going to share my screen at this point. And this is a lot of the slides come from other presentations that we as Solar System Ambassadors are privy to. We do educational telecons every couple of times a month. And there was a series of telecons about Perseverance last fall. And a lot of these slides are lifted from those presentations. So thank you, Dr. Williford and Dr. Chan at JPL for your slides. This is a title slide, for example, is one of theirs. This is actually a scene, the background here on Mars is a scene from Curiosity driving around on Mars. Sorry, Alan, I forgot to throw your name in here on the slide as well. But Alan Rich is also going to be doing it.
Name's not important.
So there's Perseverance laid out on a Curiosity mosaic of the terrain around Gale Crater. And you can see Perseverance out here with the robot arm fully extended out in front of it with all the cache of instruments up here on the turret or the business end of the arm. Now, this is a picture that Tony Rice, another Solar System Ambassador, sent us out yesterday and lifted the image of Perseverance and set it down in the parking lot in front of the Museum of Natural Sciences there. You can see the giant Earth, but you get an idea of size and scale, comparing it to the size of a minivan here or an SUV. Perseverance is pretty chunky. It's pretty big. Now, that said, you know, we're going to talk for a minute about the instruments aboard Perseverance. There's a whole boatload of them, but you can't pack everything onto a robot the size of a car. You just can't do it. For example, you can't put an scanning electron microscope, okay, on there. Too big currently. So you've got all these other instruments, and you'll notice the international flavor aboard Curiosity. You got the French, got the Spanish, I got the Norwegians here represented. as putting on components of the American-built robot, of course. But you've got all these different instruments slammed into this body of this robot, which is pretty impressive. We're going to talk about some of these instruments pretty soon. There's also some other features here. During the pandemic, of course, Perseverance was getting constructed, and they put a plaque on here honoring the healthcare professionals on the front lines of the pandemic, then and now. So thank you very much for what you're doing. If you're a healthcare worker, have any stripe, especially if you're working with COVID right now, thank you for everything you're doing. And they wanted to put this on there to commemorate that. And it's actually going to be on Mars. So you will be commemorated on Mars. And over here, there was a campaign. These 3 discs here record the names of, I think, like 400,000 people that sent their name to be included aboard the rover going to Mars. So your name, if you put it in there, is on its way to Mars, and we'll be there hopefully later this afternoon.
Mine's not on there, Ken, because last time I did that, Mars Climate Orbiter, I think it crashed. So
I understand.
I think I'm bad luck. I left my name off of this one.
Well, I put my name on the Spirit and Opportunity rovers and on Curiosity, and they've turned out well. Of course, you got the launch, which happened in July 30th of last year. The Atlas 541 launch vehicle, pretty heavy lift vehicle, send her off to Mars, So, of course, the cruise phase, which we're ending this afternoon, as it cruises and then enters Mars's atmosphere, which is what we're getting ready to do here in a few minutes. And then, of course, entry, descent, and landing. There's another whole presentation coming up later about the fine points of entry, descent, and landing you may want to tune into. I think it's happening in about an hour. But the entry, descent, and landing is called the 7 minutes of terror. And this is the time when all kinds of things could potentially go wrong. We hope, of course, that everything goes right, and we end up on a nice flat lake bed in the floor of Jezero crater. And then, of course, once it gets there, you're seeing, actually, I believe this is Opportunity, drilling into rocks here. You're seeing the robot arm work in the soil and the rocks of Mars. So the mission objectives are fourfold. Obviously, to characterize the geology of the place, to check out the delta, the rim of the crater, possibly further in inland, if you will, towards a place called Northeast Syrtis, which is another whole potential landing site for this rover, if they get the mission extended that long. But the geology, what the rocks are made of, how they're laid out, of course, the imaging, like this outcrop here that you're looking at, the Curiosity image. Astrobiology, this is a stromatolite, This is a stromatolite colony from Earth. I believe this picture was taken in Australia, but you can see how the biology has altered the minerals and the rocks and left a fossil, in this case, an algae colony. Of course, samples, which is unique. This is the first time, we're going to talk about this in a minute in more depth, but samples actually take cores of Mars and put them down on the surface of Mars to be collected later on by a future mission, hopefully launching in 2026, to go to Mars, pick up the samples, throw them in a rocket, send them to an orbiter, pick them up, send them back to Earth. So that's the sample return mission. And then, of course, some of the instruments are specifically designed to pave the way for human exploration. MOXIE and the weather station are two of those instruments. META are two of those instruments that are paving the way for human exploration of Mars. Now, we're going to go through the next several slides here, talk about some of the unique instruments that are not aboard any other machine going to Mars currently, or on Mars currently. MOXIE is the first one. Before we talk about MOXIE, though, let's talk about the JPL clean room. Okay, this place in California is pretty impressive. You can see all these people dressed for surgery here, basically. They could just as easily be working on an open heart patient, doing cardiac surgery. Masks, gloves, gowns, to protect the rover from their nasties. If this guy holding the cord over here sneezes, and he doesn't think to turn his head ahead of time, he's going to sneeze into his mask. No foul, right? No problem. This also explains why they could continue working during the pandemic, because, you know, they were already socially distancing and wearing appropriate PPE, you know, protective equipment. So, you know, the danger of contamination between the scientists and engineers was kept to a minimum. But there's Moxie. You can see it's basically a gold box being lowered into the body of the rover. Moxie's job is to take the Martian air, which is mostly carbon dioxide, and convert it into oxygen, and to demonstrate the feasibility of building a larger version of this to send to Mars ahead of human colonists, with the idea of tanking up oxygen so that they have it to breathe, they have it to make rocket fuel with, or the oxidizer for their return rocket fuel, and any other thing you could think to use oxygen for. So the enhanced cameras here, there's 23 cameras aboard this thing. And I don't remember exactly how many Curiosity had, but I think 23 is pretty close. But you can see all these cameras are color cameras. I'm not sure if Curiosity is all color cameras, but all of them are now color RGB cameras. So you'll get full color images as you're seeing. Some of these are not optical cameras at all. Some of them are X-ray cameras. In the case of Pixel, is an X-ray imager. Alan, do you have anything you want to throw in about the cameras?
They're better than Curiosities. They're higher resolution, and like you said, some of them are not interested in the visible range. It's an improvement. As the whole rover is an improvement. It weighs like a full 278 pounds heavier than its little brother Curiosity that's been up there for a few years. So, and what you talked about earlier, Ken, these are miniaturized instruments, as miniaturized as you can get them. But still, the reason for the sample return is laboratory instruments may weigh as much as a Volkswagen, electron microscopes, things like that. So these are miniaturized as good as you can get, but you still can't get Earth laboratory quality laboratory work done unless you send things that weigh hundreds of pounds up there, which you just can't do. So we're bringing some samples back, the sample return containers, in a future mission. You can do things, science on Earth, that you can't do with such small instruments. But yeah, the cameras are improved. Everything on this robot is improved, and it got bigger by 278 pounds because of that.
Okay, so the Watson and Pixel instruments also aboard the on the arm, the turret, the robot arm up here in the front. Those are not visible light cameras. Those are, I think, Watson's an infrared camera, or ultraviolet rather, and Pixel's an X-ray camera. Again, to help parse out the story of the organic molecules and the mineral constituents of the samples up close on Mars. And then Sherlock is looking specifically for organic minerals, and it's going to use fluorescence, among other things, to determine, are there organics in the rocks, and where did the organics come from? You know, are they native to Mars, or did they come from somewhere else? So that's one of the potential questions they're going to ask when they answer the organic molecule question.
One key thing to note, Ken, that it's a common question, one of these frequently asked questions is it going to look directly for life? And the answer is no, it's not. It's the only way it could actually find life on Mars is if it had an optical camera pointed and something walked in front of it. It's not directly looking for existing life at the moment. It's looking for evidence of past life, evidence of past habitability for life, things like that. But no direct trying to sniff out life or take pictures of it.
Right. Well, the one exception to that would be any like colonies that alter the rock and make the rocks, you know, basically leaving a fossil. You know, like the ideal would be to find something like, oops, it's not showing up very well, to find something like these shells in this rock here from Missouri. You know, but we're probably not going to find anything on that grand scale. If we do find life directly detected, it's going to be the microbial variety, like stuff you have to see in a microscope. Microphones. This is the second or third attempt to send microphones to Mars. And there are two different microphones, one on the body of the rover here. You can't really see it in this image because it's too up close, but the one with the red arrow pointed at it is actually on the side of the rover. And that's going to be listening to the entry, descent, and landing, along with the day-to-day operation of the rover on Mars. Now, there's a lot of things you can tell with a microphone. For example, how are the wheels wearing? If there's something wrong with one of the wheels, you might hear a squeak, of lubricant not getting to all the parts of the wheel well while it's turning, or something like that. And plus, of course, hearing the sounds of Mars itself. A windy day on Mars will sound pretty interesting. You're also going to have stereo capability because you've got another microphone on top of the mast, this white box, rectangular box over here on the left. That camera is specifically designed to listen to the environment while the laser is firing. The laser, which pops a hole in the rock, because you want to get up underneath the rust. Mars is covered in rust. So in order to study the rocks underneath, you got to put a hole in them somehow, either with a drill, which the robot has in the arm, or with a laser, which can dig about 1/10 of an inch hole into the rock and check out the substrate minerals underneath. When it hits the rock and makes contact with it, it will make a particular noise. And if you've ever gone rock hunting and you're looking for rocks that are hollow in the middle, rocks that are hollow in the middle sound very different than rocks that are solid. And so, those, if you're looking for amethyst crystals, for example, you want something hollow where the crystals are growing. And you actually tap on the rocks, you save yourself some time because you don't spend all your time banging away on rocks that are solid with no crystals in them. You hit the rocks that are hollow. Likewise, the conditions of formation of the rock will be different depending on the sample, and you'll be able to hear that difference with the microphone. Another instrument that's very unique, it's the first time a ground vehicle has this instrument on it, is a ground penetrating radar. You're going to be landing on a flat lake bed, and that may or may not tell you a whole lot, but if you can peer down into the substrate, into the rock underneath the floor of the crater, is there a glacier under there? Are there pockets of liquid water? We have no idea. But this radar can penetrate, I think it's a couple of 100 feet down into the substrate to parse out, is there any other substance in there besides rocks? Or what is the stratification or the layering of the rock in the riverbed? How's it laid out? And that RIMFAX will be able to tell us about the subsurface underneath the wheels of the rover. The sampling and cache system is a whole separate system that's brand new. This has never been done on Mars before. And the drill, of course, will take samples, a core. The drill is a hollow drill bit that's about the size of my finger. It will core out a sample, and the tube that it's coring out the sample in will be sealed, cataloged, and stored. And then the rover will dump them off in, I'm not really sure how the dumping off process works, but the rover you're going to have a set of tubes laying around on the ground on Mars. And then another robot with a fetch rover comes later in 2026, hopefully, to pick up those samples, put them in a container, and shoot the container into orbit with the Mars samples that will be returned to Earth for study here. There's a capability of taking up to 40 samples, 20 in the prime mission and then 20 in a potential extended mission, assuming it will get extended past its original lifetime. And that's a fair assumption. Curiosity, for example, was supposed to run for 1 Martian year. That was the engineering guarantee for it if it landed safely. Perseverance is a guarantee of 2 Martian years. But we can almost count on Perseverance lasting longer than that because I think it's RTG fuel, it's radioactive fuel, has a effective lifetime of about 25 years before the power levels get too low to recharge batteries. So there's your sample tubes. They're about basically the size of a pencil. And, excuse me, the samples get stored in these things, sealed, so they are effectively sterile. with whatever material is from Mars that will be going back to Earth.
One of them is going to be empty as a control sample because these tubes could be laying around on Mars for years. And you want to make sure that any gases that you find in there are not outgassed from the actual or reacted with the components that make up the tube itself. So there's going to be blank ones left.
Yeah, I think there are 42. There are 42 sample tubes, so at least 2 of them will be blanks.
Yeah,
for the control part. So landing site selection. Where is this thing going now? Like I said, there's a lot more detail. Dr. Carson, I think her name is, did an extensive presentation about the landing site and the geological context of Jezero crater on Mars. And that will be available on YouTube pretty soon, or I'm not sure what format you'll be able to see it in, but you'll be able to see her presentation that was done earlier this afternoon if you missed it. So this is a global altitude map of Mars. And so to give you an idea of context, the blues and greens are lower or as low as what's called mean sea level here on Earth. So this would be below, anything below in blue or green probably had water in it for a while. Anything yellow, red, orange, white, or brown, probably not. It's a higher elevation area on Mars, like the volcanoes that are peaked in white off here to the left-hand side of the screen. So the Jezero crater you can see up in the right-hand side there in Isidris Planitia, which is basically, it could be a bay of an ancient ocean. So you can see it's boxed in there and highlighted. There's Isidris Planitia right there. And we think it formed almost 4 billion years ago. Jezero crater is a similar age of formation. And so there's a up-close view of Jezero from orbit. You can see the kilometer scale there in the lower left. So we're down to pretty high resolution here. We're looking down into a riverbed and a delta. Now the riverbed, I'm having trouble with my cursor pointing us off in the upper left-hand side here. And you can see it kind of snaking its way into the crater. The crater here in the middle and the right. This finger-like projection with all the different colors in it is a river delta. Now, river deltas take a long time to form. They take, in this case, probably millions of years to actually form when a river is flowing into a still body of water like a lake. And in this case, and the river dumps its load of sediment, of mud and sand and everything else. And over time, it forms a delta that has some appreciable height. This one in places is several hundred feet tall. So it's a pretty big delta. And you can compare it to an Earth analog would be the southeastern coast of Louisiana in the United States. That's where the Mississippi River enters the Gulf of Mexico. And over millions of years, all those finger-like projections sticking out in the coastline of Louisiana are parts of the mud and the silt dropped by the Mississippi River over a long period of time. You can see a couple of impact craters here in the delta itself. That's going to be, if they can get Perseverance into there, that would be a very interesting place to examine, to look at the layers inside the delta itself, or some of the impact craters on the floor of Jezero crater. These little circles here might be a good place to look. Like where an Opportunity explored several of the craters it met along the way on Meridiani Planum a few years ago. It found a lot about the Martian geology, subsurface geology, by driving down in there. Oh yeah, sorry. The colors here represent different rock types, okay, or mineral types. The purples and blues and yellows are clay minerals, and the green is limestone. And so, it'd be very interesting to see what the limestone here is made out of. You go to a place like Florida and you pick up a rock, it's made out of limestone, and it's got all kinds of creepy crawlies in it that used to live there. It's basically one big fossil. So it'd be interesting to see if that ends up being the case here on Mars. We don't know. So entry, descent, and landing. Again, there's another program all about this in about an hour. But at first glance, the entry, descent, landing here looks a whole lot like Curiosity's about 8 years ago. You've got a sky crane pictured here, the back shell with the jets firing down, and the rover itself being dangled down by these tethers or cables. So you can see the landing ellipse for Perseverance is much, much smaller than any previous rover. You probably couldn't land Curiosity here. And the rover, as it's coming down, takes descent images, compares them to orbiter images taken by the Mars Reconnaissance Orbiter and other orbiters in its onboard computer, and makes a determination, is this a rough area to land or a smooth area to land? If it's a rough area, it can actually fire its rockets to scoot along the surface to get down to a place where it's going to land in a smooth environment, kind of like what Neil Armstrong did when he negotiated a field of boulders and passed it to land Apollo 11 safely on the moon.
Ken, interesting to note here that this is all done autonomously with the Sky Crane, its own AI, because of this. There's no help from humans while it's doing this. The signal strength, the signal distance is light speed from Mars to Earth. And how many light minutes is it going to be when this happens? About 8 light minutes?
About 10, yeah.
Yeah, so it's a round trip of the signal so long that, you can't, people think, oh, there's probably somebody sitting behind Ken in mission control there with a joystick. And say, turn left, turn right, go up, go down. Don't land there. No, this whole landing procedure, the decision on where to land, is done completely by the robots with no help from humans whatsoever.
You can think of it like an intelligent dart. NASA will puts it on the right trajectory to enter orbit and enter the atmosphere in the right place, where it ends up landing in that ballpark, in that landing ellipse we talked about a minute ago. From then on, once it gets close, once the heat shield is separated off, and the rover is looking down at the ground with its cameras and its radar, it's all up to the rover to figure out where exactly to land within that larger context of the floor of the crater. So again, you don't want to land where the bumpy stuff here is in the left-hand side of your ellipse. You want to land in the smooth part there to the right. So that's hopefully where she'll end up, is somewhere in that lake bed near the delta, but not on the delta. And this is an image that shows how the rover actually compares surface images to orbiter images that it's taken itself to come up with a smooth landing site.
Again, the same procedure that we used to land Curiosity a few years ago, which differed from the 2 robots, Spirit and Opportunity, before that, which, if you remember, instead of this sky crane maneuver, they inflated airbags around themselves. So they got dropped onto Mars and then bounced several times and came to a rest. The airbags deflated and they came out. Well, the reason why we can't do that with Curiosity and now with Perseverance is because these are much larger, heavier robots. Yeah. And the airbag deal just wouldn't cut it. So you had to have something else.
So these are all the cameras that are going to be involved just in entry, descent, and landing. You've got a camera that sits on top of the back shell, on top of the jetpack, if you will, that's looking up at the parachute. You got another camera on top of the rover that's looking up at the back shell. So what you're going to end up with, along with the microphones that are attached to the rover, you're going to end up with, in a few days after the landing here, the sights and sounds of landing on Mars, from when the parachute opens up all the way down to the actual landing of the robot, and the cutting of the cables and the fly off of the back shell. So you're going to be able to see all of that. And obviously, the engineers will have a field day with all that information, analyzing what went right, and more importantly for them, what went wrong, so know what to fix for next time. To make it even better for an even bigger rover or human spacecraft. human populated spacecraft to land safely on Mars. So this is all data for those guys and gals. And it will also be very, very interesting stuff for you and I, the casual observers. Now, of course, we're not just landing a rover on Mars, are we?
The first helicopter ever deployed by mankind anywhere besides Earth.
Yep. So 5 test flights are going to happen sometime 50 to 90 sols or days after this thing lands on Mars. When right now, the Ingenuity helicopter is attached to the bottom of the rover. So for the first month or so, you have to imagine the rover driving around with this appendage sticking out underneath it. So they're going to want to get rid of that helicopter as soon as they can and put it safely on its own on the surface of Mars. But once they do that, because it will impede where the rover can go, because you've got this thing sticking down from the base or the belly pan of the rover. So it has to affect where they can drive and where they can't drive. So as soon as they can do it, they're going to deploy the helicopter, and the rover and helicopter will communicate back and forth, and the rover will fly the helicopter, basically. So the rover will, you can think of the rover with a joystick, actually inside of it somewhere, an imaginary joystick, flying the helicopter. Basically, go ahead.
Excuse me. The helicopter transports underneath the belly of the rover in what looks like exactly like the oil pan of a car. And I was doing a presentation about this once, and I said, that's the rover's oil pan. It holds 10 quarts of Castrol 10W40. And some people are like, what? It looks so much like that, they believed me.
Yeah, so the helicopter's basic job is to take pictures where the rover can't go. Now, obviously, if this technology works, if this is a successful demonstration, bigger and more well-equipped helicopters will fly on future missions, because a helicopter gives you an entire different dimension of exploration here on the ground. You can't, for example, you probably can't drive the rover straight up this cliff right here, but you can land a helicopter up there and take samples if you were actually had a sampling arm on the helicopter or whatever in the future. But for right now, the helicopter is just proving that this technology can actually work on Mars. But before they send it to Mars, you got to make sure it works in a Mars-like environment, a simulated environment on Earth. So you got this room here where they suck out most of the air, make a Mars atmospheric pressure, which is about 1% R pressure. You cool the air down to about minus 20 degrees Fahrenheit, and then you see if a robot will fly in that condition. And the answer is yes. So our helicopter weighs in at about 4 pounds. The blades spin upwards of 3,000 RPM to get it fast enough to actually provide lift. It's solar powered, so the batteries get recharged courtesy of the solar panel up here. You got batteries, cameras, and all this other stuff stuffed into this little box here, the body of the helicopter itself. And then, of course, the landing pads. So, the helicopter provides just another whole dimension of Mars exploration that we haven't had before. As Alan pointed out, this is the first time. So it launched on July 30th, and it's supposed to be saying landing February 18th here. I'm not sure what happened to that, but that's today, boys and girls, and ladies and gentlemen. So hopefully in about an hour and a half here, we're going to see a landing on Mars. And if you have any questions about all of this, please put them in the chat. we're going to be doing a question and answer session. All of our presenters this afternoon will be hanging on for a question and answer session once the landing feed stops from Mars around 4:10 this afternoon. So stay tuned for that, and good luck, and everybody find your dry roasted peanuts.
Yeah. A couple of things I wanted to add, Ken. Great presentation you put together here. A couple of more frequently asked questions is, how is the robot powered? If you remember back, the previous generations of robots were solar powered, Spirit and Opportunity. They had these things that looked like wings that were solar panels. And the missions were only supposed to last 90 days because Spirit and Opportunity, it was thought that you'd go into winter and you wouldn't get enough light to the solar panels, and Mars is dusty, so you would get dust all over the solar panels. But Mars is also windy, so it kept the solar panels clean, and we got 8 and 14 years out of those robots that were only supposed to go 90 days. But Curiosity, the current generation, Curiosity that's already been there for a few years, and its big brother Perseverance landing here shortly, they're bigger and they have more energy requirements, so they're actually nuclear powered. No solar panels. The helicopter, as Ken mentioned, is solar powered, but the actual robot itself is not. It's nuclear powered. Back on the back of it, there's a thing that kind of sticks up like a ducktail, and inside that is a chunk of plutonium-238 that literally glows. It's radioactive, very, and it literally glows red for a couple of decades. And it's, I think, right now, it's almost at 300 degrees Fahrenheit. So you take, well, maybe that's Celsius. I don't know, but it's hot enough for a chunk of metal to glow red. And there's two things that happen. You use thermocouples to convert the heat directly into electricity. And you also have tubes of what's essentially antifreeze, the same thing, ethylene glycol that's in your car radiator, that circulate around it and pick up that heat and transfer the heat in the liquid antifreeze to components of the robot that need to be kept warm, because Mars can get pretty cold at night. So nuclear powered robot, same as Curiosity, it's little brother. The other frequently asked question is, how does it get to Mars, and why does it always seem to take like 8 months? Everything we send to Mars, everything anybody sends to Mars takes like 8 months. There's an orbital trajectory called the Hohmann transfer orbit. And it's basically rocket science 101, how you get from one planet to another. You achieve, leaving Earth, you achieve escape velocity from Earth, which is like 22,500 miles an hour. That's the speed you need to get to permanently escape the gravitational influence of the Earth and get away from here and go someplace else, rather than just put yourself in Earth orbit. So then when you do that, though, you're in orbit around the sun. And as long as you don't do solar escape velocity, which would be 40-something thousand miles per hour, you'll just be in orbit around the sun like all the planets. So you time all of this so that the orbit of the robot intersects the orbit of Mars when Mars is there, hopefully. And that's basically how you do it. It's called the Hohmann transfer orbit. And that's why that orbit, that trajectory takes about 8 months. And if you try to go any faster with a big rocket, it doesn't really help, and you can't go any slower or you'd stay in Earth orbit. So whatever country sends things to Mars, it's give or take a few weeks, about 8 months.
And speaking of countries, it's important to note that there's a couple of new nations that have entered the Mars exploration game. The United Arab Emirates and China have both successfully entered orbital insertion with their vehicles that are going to explore Mars. Now, UAE's spacecraft Hope is going to be an orbiter, but it's orbiting at a distance much further away than any of the any of the other Mars orbiters. So it's going to get a more global perspective of weather and climate on Mars. The Questions to Heaven, I don't know the Chinese for that, but that's the name of the robot that China sent, is in May, similar to the Viking system that we launched back in the 70s, is going to send a lander and then a rover down to the surface of Mars in May. So it's going to wait a couple of months and then deploy the lander and rover setup down to Mars. And hopefully that works. And China enters that very rare club of explorers that can drive around on Mars. That's a club only currently being done by the United States, by the way. So that's right now, it's a point of American pride that we're the only ones to drive on Mars so far.
It's quite hard to do. Mars tends to eat spacecraft and robots. It's
exploration.
Less than half of the historical attempts to go to Mars have worked out well.
Mm-hmm. Yeah. Yep. It's very rough.
Okay.
Okay.
That it?
I think that's it. Thank you very much for tuning in. And hopefully, if you've got questions, throw them in the chat, and they'll be compiled by the museum staff, and we'll get to ask those questions at about 10 after 4. So tune back in. Obviously, you want to watch the rest of this because we're going to be landing. They're going to be landing a robot on Mars here in a little bit. You want to see that. So thanks for coming.
Yeah, thanks everybody, and stay tuned. The landing is coming up.
Check 1, 2. Hey, everybody. All right. We are getting so close to Perseverance landing on Mars. It's going to happen in just a few minutes. Alan, can you set up the final presentation of the day for us?
Yes, we have a presentation from a couple of solar system ambassadors, Mark Fusco and Ken Brandt, on EDL, entry, descent, and landing, which is what's going to happen here starting in about 30 minutes. And then we're going to show you a video of, because we can't see in real time, we're going to show you an animation video of what's happening as it is actually happening. It's going to be a parallel to what's happening, but since we can't see it, we got to show you a video. And then after that, we have to wait 11 minutes for the robot to send us back a signal that it's on the ground safe, and then we'll do that. So this is all going to happen within the next 45 minutes, and we need to get rolling. So let's watch it. Eat your peanuts.
Hey everybody, I'm Mark Fusco, Solar System Ambassador here in Raleigh, North Carolina. I'm here with my fellow Solar System Ambassador, Ken Brandt.
Hi everybody.
Ken, what is your title?
I'm the director of the Robinson Planetarium in Lumberton.
All right, thanks for joining us today. We're here to talk about the exciting event that's coming up in a few minutes, the landing of the Perseverance rover. Now, it is a very important mission for NASA. It's a very important mission for science. And the most critical and at the same time most exciting portion of the mission to date is about to unfold, the entry, descent, and landing. So I wanted to tell you all a little bit about why it's so hard. Mars has an atmosphere, as does the Earth. Mars' atmosphere is 100 times thinner than the Earth. So parachutes don't work the same way they do here. There's no effective way to slow down the way we would slow down on Earth or on Venus or any planet with an atmosphere. So we had to take care to devise a way to get a 2,000-pound rover onto the surface in working order. So we're going to talk about exactly how that works. Ken, would you like to add anything before we jump in?
No, you got it.
All right. So I am going to share the screen. Away we go. All right. Entry, descent, and landing. So we've had a history, we at JPL have had a history of sending rovers to Mars. We've had three series of rovers so far. Open a laser pointer here. We had the Sojourner rover in 1997, which was relatively small. Then we had an improved model, a Mars exploration rover, Spirit and Opportunity, who we landed on Mars in 2004. Both of these classes of rovers were a lot lighter than Perseverance and Opportunity. And the way that we landed them is we had them come in into the atmosphere, used a very large parachute. And then right when it was about to land, we inflated a bunch of inflatable landing bags around the rover. So in essence, it was encased in a beach ball, for lack of a better metaphor. And when it touched ground, it bounced until it eventually came to a landing. Then the landing bags were deflated and the rover could begin to work. Now, we can't do that with Perseverance. Hey, everybody, I'm Mark Fusco with Solar System. But I watched it. It was a beautiful launch. And then Perseverance was then on its way. Now, while it was flying to Mars, the Perseverance rover was in a very nice package. You can see the rover is right here, and it's all folded up. Its wheels are folded up into its compact state. Attached to it is what's called a descent stage. And this descent stage is the piece of equipment that will actually take the rover the last mile down to the Martian surface. So this entire thing, this cruise stage up top has all the navigation equipment and all the technology that's needed to get it from Earth to Mars safely. The equipment is inside this clamshell. We have the back shell, which is the top shell, the descent stage and the rover, and then there's a heat shield on the bottom. So think of it as a clam safely inside of it. And the heat shield will protect the rover itself from the extreme reentry heats. So, all right, let me turn this off. All right, so the cruise stage is abandoned right before the Perseverance rover package, the clamshell package, hits the Martian atmosphere. It hits the atmosphere going 13,000 miles an hour. Now, while the Martian atmosphere is 100 times thinner than that of Earth, that's still pretty fast to be hitting any atmosphere. So what will happen after it hits it, it comes in with the heat shield first. So that's taking the brunt of all the energy from the atmosphere. And the aerobraking from the heat shield will slow the spacecraft from 13,000 miles an hour down to about 900. And during that time, the heat shield will reach upwards of 4,000 degrees Fahrenheit, meaning that the rover needs to be protected. Well, this is designed in such a way so that even though on the outside it's 4,000 degrees, the rover itself never gets hotter than room temperature, about 72 degrees. So it's nice and cozy tucked in there. At that point, when it's 900 miles an hour, a supersonic parachute opens. It's one of the largest parachutes ever built. Designed and built. It was designed just for this mission, just for these conditions. It will slow the spacecraft from 900 miles an hour down to 180 miles an hour, which is about how fast a NASCAR car drives on a straightaway. The heat shield is no longer needed, so that's jettisoned, that's extra weight. It's dropped, and when it's dropped, you can see in the bottom left of the photo, it's exposing both the rover, but more importantly, all the landing instruments, altimeters, things that are going to be used to deliver the rover to the proper place. When it's down to about 200 miles an hour and a little less than 1.3 miles from the ground, 4 engines on the corners of the descent stage, you can see them, and they're kind of tilted at an angle away from the rover as to not affect it. But they will fire, and it, in essence, becomes a flying platform. And then it separates from the back shell. So it's flying all by itself. And at that point, it begins looking for a safe landing place. Now, it's around a little over a mile off the ground. Again, it's traveling about 200 miles an hour. The platform will stabilize the spacecraft, slow it down even more so, and then it begins, it flies it to the last mile to the Martian surface. So it's identified a landing site that's not, there's no cliff, there's no boulders that it can land on, and there are no boulders surrounding it, so it won't be able to drive out. It avoids all those type of situations.
Mark, can I throw something in here a minute?
Please do.
Okay. A couple of things are happening as it's coming down on this Sky Crane platform. There's something called terrain relative navigation that's happening. The rover takes images of the ground, compares them to an image library of orbital images taken of the crater by other spacecraft that orbit Mars, like the Mars Reconnaissance Orbiter, and compares them and uses that information to steer away from potential rough spots like the delta within the crater itself, to find a smooth landing spot somewhere out on the lake bed. And we'll talk more about the lake bed in a few minutes. But thank you.
Thank you. Very insightful. So we're less than a mile from the surface looking for a place to land. And what I consider the most exciting part of this, the whole operation begins. The descent stage lowers the rover on 3 cables it calls a bridle. And you can see there's a 4th kind of squiggly cable there. That is electronics and communications cable to keep the rover in contact with the descent stage. So it will lower it down via the sky crane, and it lowers it, and then it kisses it down at a nice 2 miles an hour. So we've gone from 13,000 miles an hour to 2 miles an hour in about 7 minutes in the most extreme conditions you can imagine for landing. Now, at this point, they're still connected. So we have a rover on the surface, and we have a flying platform with 8 rockets firing. So we need to disconnect the two. So what happens is Perseverance will cut the cables using explosive charges attached to a guillotine. We'll cut the cables. Perseverance is in its landing spot. The descent stage flies off 100 yards or so and is deliberately crashed into the surface. And Ken, would you mind describing what type of data we're going to be collecting at this point after we crash the platform?
When the platform crashes, it's going to generate seismic waves, kind of like a very small earthquake, or Marsquake in this case. And the InSight lander, located a couple of 100 miles away in another part of Mars, will actually record the pattern of those waves as they arrive at the lander, and use that to generate more information about the Mars crust. Because the InSight lander has been operating on Mars since 2018, measuring Mars earthquakes and other things about Mars's environment. So that'll happen, so it's kind of like a 2-for-1 experiment. Not only do you get this thing down safely to the surface of Mars using your sky crane, you also crash a landing platform, and that generates more data for another mission, which is kind of cool.
Right, and NASA and JPL do this on a lot of planetary missions. It's something that we've been doing since the late 60s. We've done it on the moon, we've done it on Mars, and it gets us more data about the actual geology of Mars. So that's exciting. So we have Perseverance on the surface. This is unfortunately a photo of Curiosity. I don't have a photo of Perseverance on the surface because it's not there yet. But what it will do is it will send a selfie to Earth announcing its arrival. Hey, I'm here. Everything's working. And then you'll see the people in the control room high-five each other and just celebrate it. They've been working on this for years. The EDL folks have been working on this. They've been watching this for 7 months. This is the big moment. Now, one thing I wanted to talk about is we call this the EDL the 7 minutes of terror. And it's not a terrifying landing. The terror comes because it's an asynchronous landing in the sense that it takes, let me turn this on. It takes about 7 minutes to get from here to get to here, to get to the landing. But it also takes 7 minutes because the Earth is far enough away from Mars that the data, the communications, traveling at the speed of light will take about 7 minutes to get to Earth. So that means we're not watching everything in real time back at mission control. So when Perseverance sends the message that, hey, I just hit the atmosphere, when we get it 7 minutes later, Perseverance is down on the surface already. So we will have a 7-minute delay. So we don't know if everything's going right optimally or not until 7 minutes after the actual landing. So that's the actual 7 minutes of terror. It is nerves. We expect it's a very elegant engineering solution for this. And right now it's 1 for 1, and we anticipate it to be just as successful this time. Let me turn that off. All right, and then we have the Perseverance lander on Mars in Jezero crater, ready to go to work. Now, where are we going? Why Jezero crater? Here's a photo landing site, and I'd like to turn it over to Ken Brandt. I will stop my share here, and Ken has a presentation on why we're going there and what's there. Take it away.
Okay, I'm working on that now.
Right.
Let's see. Here we go. There's that. All right, so the yellow ellipse here is the landing ellipse for the Perseverance rover. And it's important to note that we could not have landed any of the other rovers in Jezero crater. Jezero crater is just too small. It's only 31 miles wide or so. So, Curiosity's landing ellipse was larger than that. I think I've got a slide here that shows that. But let's do some context here. We're looking at the planet Mars as in elevation relief. So the redder and whiter the colors are, like these volcanoes over here, the higher the terrain is off the ground. So if we look for the blues and the greens, that's probably where the water was a long time ago. And Jezero crater looks like from a global view here, looks like it's inside of a bay, or right on the edge of a bay here, in what would have been a global ocean a long time ago. So we're going to focus in on that. Now you can see the bay. There's the bay, and there's Jezero crater, this little crater off to the side of the bay embayment. Isidrus Planitia. Now this is Jezero crater done in geological map style. So you've got black and white images that have been mosaiced together, several dozen images stitched together. And we see some features here that are worthy of note. Again, our landing ellipse is out here somewhere. That's where we want to land, out here on the lake bed. Lake bed, being a lake bed, is relatively flat and very unremarkable terrain, hopefully. Got a couple of little craters here you probably want to avoid. And this little bump here, or whatever that is, probably don't want to land there. So that's what that terrain relative navigation will do for you. As you get closer to the actual landing site, it will avoid some of these rougher areas and find a nice smooth patch to land on. Okay, but these colors represent different geologies, different mineral bodies here. For example, the greens here represent limestone, calcium carbonate. So you can see calcium carbonate remnants all throughout the lake bed and the delta here, this fan shape here. And that delta is pretty important. It tells you a couple of things. Thing one, it tells you that a river ran into this. And you can see the riverbed here oxbowing its way into Jezero crater. The riverbed doesn't just happen between now and 6,000 years ago. That happened a long time ago, and it took millions of years for that to form. The other thing, this delta doesn't happen between now and last week. This happened over millions of years. You've got river water flowing out into a lake. When the river meets a still body of water, it drops its load of sediment and mud and everything else to form a delta. The Mississippi Delta in southeastern Louisiana is an excellent Earth analog to this structure. The Mississippi Delta, of course, is a lot larger because the Mississippi River was a lot more water flow than this little river here. Still, we got a river flowing into it. On the other side of the crater, there's an outflow stream, or several of them, that outflow into Isidrus, Planitia. So we had running water here. And running water on this planet equals life. You know, you look for evidence of fossils in places where water ran through it. That's a good place to look, for example, for shark's teeth, like in North Myrtle Beach or in Wrightsville Beach here in North Carolina. These are good places to look for shark's teeth because you've got sediments that were laid down in an ocean a long time ago that get washed up on the beach, and you find shark's teeth all the time. So are we going to find something like this on Mars, these shells in here, inside this shale rock, this lake bed rock here? This comes from Missouri, okay? You see a spiral shell right there. Who knows? I doubt it, frankly. We'll probably find fossils that are a lot smaller, like microscopic fossils or colonies of algae. There's actually some evidence that some of the formations that Curiosity and Opportunity, two other rovers, saw on their traverse were actually algae colonies, algal mats. But neither rover had the instruments aboard to actually measure to see if there were fossils there. Now, we talked about landing ellipses earlier. Inset here is the Perseverance landing ellipse. There's the Curiosity landing ellipse. Curiosity would have a very hard time landing on this lake bed using its landing technology of 8 years ago or 9 years ago, 8.5. But you can see these much larger landing ellipses that just would not permit a landing in Jezero crater at all. So, all the additional technology that NASA has been able to import into this rover and the computing power that the rover has available to it to actually process images in real time makes a big difference to how big our landing ellipse can be. And there it is again. So like I was pointing out, you couldn't land Curiosity in here. So the upshot of all this is NASA, after an extensive process of selecting down 64 landing sites, think of the NCAA basketball tournament, okay? Jezero crater made the final four back in 2018, along with places like the Columbia Hills, which was visited by the Spirit rover. NASA actually had thoughts about sending Perseverance back to the Columbia Hills to search for more evidence of life up there. This looks like one of the better places to actually look for evidence of ancient life, though, for a couple of different reasons. The lake bed itself will provide the opportunity to find algal colonies or microscopic organisms in the body of the lake bed itself. Because the lake bed, as we've seen in Curiosity's imaging of Gale.
All right, everybody. Hey, we're back. Chris with the North Carolina Museum of Natural Sciences and Alan Rich, NASA-JPL Solar System Ambassador. We are breaking in now towards the end of this presentation because my nerves are on edge. Alan, how are you doing?
Yeah, I'm eating peanuts. My nerves are on edge too. Don't see the video, but Mission Control, EDL has just started. The 7 minutes of terror have, there we go. The 7 minutes of terror have
36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now
one of the
Performing bank
navigation
reversals
tabs.
in the
So
atmosphere.
we just switched
These
over
are
live
the
to
steps in
NASA
order
video
to
control.
distance to the
JPL
landing
in
target.
Pasadena, mission control for the landing. They have their own animation here.
The point of
We can
maximum
watch.
All right.
deceleration and has indicated
We're going to
that
turn it over to the
it's
folks at
held
Mission Control.
approximately 10 Earth Gs of deceleration.
MRO has lock again.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target. Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, to the target on Mars, but instead is flying straight to the target.
Parachute.
When it hit the atmosphere, it was going a little over 12,000 miles an hour.
And 50 meters per second at an
The
altitude
first
of
part
about
of
15
EDL, of
kilometers
course, will be
from the
to
surface.
aerobrake like a meteor or a spacecraft entering, scrubbing off speed with
MRO is
friction.
reporting good telemetry lock.
We're down to Mach about 5, we're now at Mach 3, which is 2,100 miles an hour. The parachute will open, I think, at 940 miles an hour, which is supersonic.
In preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Yes.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Do we have audio from this? Okay.
Yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
Got it.
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Almost there.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation. We have timing of the landing engines. Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a
Just
kilometer
confirm that
off
it
the
is
surface of
decided where
Mars.
it wants to land.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
Oh my God. Oh. Oh.
MRO reports they're still getting telemetry from the lander.
All right, all stations.
We got it.
Touchdown confirmed. We're going to wait for the images.
Wow.
This is so exciting. The team is beside themselves. It's so surreal. Stay tuned. We might get some pictures.
That'd be great.
So much has been riding on this.
Yeah, we just heard the news that Perseverance is alive on the surface of Mars.
It's not the
Flight, we have seen the completion of EDL 3000. Copy activity. That is as expected.
MRO is still seeing a strong signal from the lander.
We have just heard the news that Perseverance is alive on the surface of Mars. Congratulations to the mission. And looks like we have some more news in. It looks like we're getting the first image. Here, take a look at the first image.
Everyone who's tuned in to the North Carolina Museum of Natural Sciences YouTube,
I have
we
the
are
target point
successful.
on the map.
NASA just landed
We are ready,
Perseverance on the
OL3.
surface of
Go
Mars.
for it.
Just can't stress enough how difficult that is. It's the second time that's ever been tried. It's an amazing feat.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
The team has just put the first image from Perseverance on the surface of Mars. Now, it comes from the engineering cameras, known as the Hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
Wow, okay. I didn't think it would be emotional, Alan, but here I am. Well, I can say from the Museum of Natural Sciences, congratulations to the entire NASA-JPL Mars 2020 team on a successful landing.
We have our first image here from one of the 23 cameras on board, the navigation camera, I think. Not a very good one, but what can you expect?
Yeah. Wow.
We just got our second image in. Our second image
Wow.
is in.
Okay, these we have a camera in the front and rear of the spacecraft. They're near the ground, so these are pretty close. So you can see the wheels there, and they're a little dirty because we've got glass covers over these cameras. But we took these seconds after landing, so there's still dust in the air from our landing event. So this is happening. This happened just seconds ago. Just arrived, and this is really amazing. And we even know where we landed. This is the most amazing thing. The vehicle has told us where it's landed because it figured it out. This is a sign. NASA works. NASA works. And when we put our arms together and our hands together and our brains together, we can succeed. This is what NASA does. This is what we can do as a country. On all of the problems we have, we need to work together to do these kinds of things and make success happen.
Joining us now is the acting administrator of NASA, Steve Jezero. Steve, welcome and congratulations.
Hey, thank you. What an amazing day.
And how does it feel to have another rover on Mars?
It's amazing to have Perseverance join Curiosity on Mars, and just a credit to the team. I mean, just what an amazing team to work through all the adversity that goes and all the challenges that go with landing a rover on Mars, plus the challenges of COVID, and just an amazing accomplishment.
And what does this mean for NASA and its future plans?
So for robotic exploration, every time we execute a mission with new instruments, we discover new things and things we never thought we would discover. So that always informs our future robotic missions, both landers, rovers, and orbiters. This mission also has technology on it. One of the cool things is the Ingenuity helicopter. It's an experiment on this mission, but if it's successful, we can use it as an science observation platform by putting instruments on it, and also use it as a scout for future rover missions, and then just the entry, descent, and landing capability. It'll allow us to land more larger, more ambitious robots on the surface of Mars, and then for human exploration. We have the Mars Entry, Descent, and Landing Instrumentation, which is going to give us EDL information. We have the Mars Environmental Dynamics Analyzer. It's going to give us size and properties of dust particles, because when we send people, we're going to have to deal with that dust. This is just an incredible mission because of the science and the technology, and then caching samples for a Mars sample return mission. That will be an amazing mission, the first round trip to Mars and back, and bringing those samples cached by Perseverance back to Earth to examine with state-of-the-art equipment in our laboratories here on Earth.
We have so much to look forward to. And we also have a student question coming in from Landon. Let's take a look.
Hi, my name is Landon Applegate. I'm in 6th grade, and I'm going to Academy for Academic Excellence. And my question is, do you think we could get resources from Mars to help on future missions, or even as like a launching point?
Great question, Landon. Actually, we have an experiment called the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, and it's going to demonstrate generating oxygen from atmospheric CO2, and that could help generate breathable oxygen, and even if we can liquefy it, oxidizer for propulsion systems. So that's a tech demo on Perseverance. And then we're going to continue to characterize the frozen water on and below the surface of Mars, and eventually try to figure out how to extract that water from the Martian soil, or what we call regolith. And then we can use that for potable water and also break it down into oxygen and hydrogen for rocket fuel. So absolutely, we're going to try to eventually figure out how to live off the land to support human missions to Mars.
Thanks for taking the time to talk to us today, Steve.
Thank you.
And now that Perseverance has safely touched down on Mars, let's learn more about what's in store for the rover. Joining us now is Surface Mission Manager Jessica Samuels. Jessica, your surface operations team has now taken over. What are they doing now?
Yes, hi Raquel. We are so excited here in the Surface Mission Support area. The team will do a handover with the entry descent landing team. And
well, Alan.
Well, Chris,
congratulations.
JPL's motto is "Dare Mighty Things," and we sure dared this one and did it. And remember, Mars is the only planet known in the universe that is entirely and exclusively inhabited by robots.
And ones that we sent there.
Yeah.
That we know about.
That we know about.
That we know about. All the ones that we've come across. Well, so Alan, give me what are your initial thoughts right now? We just got successful confirmation that Perseverance is ready to roam the surface.
Oh man, it's a really emotional moment. This was such you just worry about this. It was such a hard thing to do, and we only done it once before. So I'm like, oh no, what if there's so many things that could have gone wrong. So many things that could have gone wrong. If we hadn't got this touchdown safe signal, it could have been anything from a minor issue that the spacecraft detected some little insignificant problem and went into safe mode, or it could be that it crashed, and anything in between. But we wouldn't know. We'd be sitting here right now. Why didn't we get the signal? Why didn't we get the signal? But we got the signal. It said it's safe. It said it's home. And it is home, actually, now. It's not Pasadena, because this thing was designed to live on Mars. It is a Martian robot, and it is home.
I'm really excited. I mean, now we've just hit this great milestone, and now the real work begins, doesn't it? I mean, like building, assembling, planning the launch and the landing. I mean, it has taken a lot of time, a lot of effort, a lot of money even to get to this point now where we can dig into the surface of Mars even more to learn more about its ancient history.
Right. And, when you talk about a lot of money, I'd be remiss without mentioning that one of the big efforts that NASA makes is to take the money that you pay with your tax money and do a spinoff return on, not a spinoff return, do spinoff returns on that in the field of medicine, aircraft, automobiles, in so many different fields. You get an incredibly huge return on your investment into NASA. So it's not just to satisfy our curiosity for space and Mars and launch rockets and do those things that we enjoy doing. It's for everybody. The return on investment is huge, and the quality of life you have and the things you enjoy from the spinoffs from the space program is enormous. And I just had to mention that.
Excellent, excellent stuff. Well, folks, I hope that you're still tuned in with us, because now we're going to move into the part of the show where we want to take your questions. People have been dropping questions in the chat box all day long. I've got them all archived here so that I can start sharing them with many of the guest speakers that we had today. So I'm going to invite all of our NASA-JPL Solar System ambassadors who you met and heard from today into our program. Let me introduce them one by one. Of course, you've met Alan Rich here with me, but also today you heard from Sean Bale, Ken Brandt, who's also director of the Robeson Planetarium, Sarah Taylor, Matt Funke, Mike Keefe, Mark Fusco, Doug Lively, and I hope I'm not missing anybody.
There was Tony Rice, who's not with us, and I got to mention too, if you like this kind of thing, he contributes to WRAL in the weather department of WRAL. You kind of think, well, where would you put space stuff on a TV station? It wouldn't be with sports, I guess. Well, it's with weather because that's up there. So if you can follow Tony, he's active on putting what's going on in space on the WRAL Weather Center blogs. So look for him there. He wasn't able to be here with us for this, but got to mention great work he does there.
Absolutely, absolutely.
Nice touch. Nice touch.
Yeah. So I've got some questions here. I'm going to get to those in just a second. But if we can do just like a round robin really quick, I just want to get everybody's initial reaction. Just take a few seconds, share with us. And I'll just go in order on my screen here. It looks like, Ken, you're up first.
Oh, yeah. We're on Mars, baby. Ow.
That's brilliant. That's brilliant. Sarah, how you feeling?
Yeah, welcome to Mars, Perseverance.
I see you put up a banner too.
Yeah.
And it says
change of scenery. Mm-hmm.
That's so much fun. It's a Mars party now.
Yep.
Sean, how you doing over there?
I'm fantastic. I mean, how could it not be? What an amazing accomplishment. And you asked me how I'm feeling. I just ate a half a jar of peanuts. That's how I'm feeling.
Yeah. Matt, what are you thinking about right now?
I tell you, I'm just absolutely ecstatic about this. Considering all the planning it takes, as Alan pointed out, it's only the second time we've tried to land a rover this way. It's just stunning that we were able to do it. And I can't wait to find out what it is that Perseverance uncovers for us on this red planet.
Excellent stuff. What about you, Mark?
I am exhausted. This has been a long journey for all of us. The buildup is almost too much to take, but I couldn't be happier. And I wanted to thank the thousands of people who worked on this project, brought it in safely, who are not going to be mentioned. They all do this type of work every day, and we owe a lot to them. Just keep in mind that this is only the beginning of Perseverance's journey. I was glad to be part of it. Thanks.
Excellent stuff. What about you, Mike?
I'd have to say proud. I mean, this is a huge accomplishment. We're only doing it the second time during a really, really difficult year that we had last year, and it takes tremendous cooperation. So just ultimately, wow, really, really proud.
And last on my screen is Doug.
Yeah, I have to say, with Mike, super proud of all the accomplishments that our country and many other countries put into this in terms of cooperation, design of parts, materials management, engineering, working through all kinds of just the minutia of problems and engineering hurdles that you have to cross in doing something like this. It's just incredible. And not just this, so the point of landing, as someone said, we all said earlier, any one thing, just a small short, could have just completely ruined the project. Just to see it execute flawlessly, on target, on time, in the right place, it's incredible. Looking forward to the science that's coming out of this in the coming days, weeks, and months, and I'm really super excited about it.
Thanks so much, everybody. Go NASA. Yeah.
We've got to mention too, kudos to the engineers and scientists at JPL in Pasadena. They've got a history of doing things that the last two Mars rovers were only supposed to go for 90 days, and they went 8 years and 14 years when they were only supposed to do 90 days. JPL scientists and engineers all go, this is only going to work for a couple months, and then it works for a couple of decades. And they've done this with other missions too, and they're just an incredible, they've got the best rocket scientists and rocket engineers in the world.
You're here.
And
I'll second that.
You know, Chris, those robots are not exactly operating in nice conditions. These are very harsh conditions, either the deep of space or on a planet that we're learning a lot about, but we also have a lot more to learn, and temperature variation and dust storms and dust devils and quicksand traps and just incredible amount of adversity. And these rovers just make their way through it for decades. It's amazing.
And I think it's worth saying that, you know, there was the old adage that Mars eats spacecraft. So, I mean, again, just impressive, just doing it for the second time.
Absolutely. So let me get to some of our viewers' questions. I'll try to pop these questions around and get everybody involved here. But if you think you've got a better answer than somebody else, holler at me, like wave, let me know, and I'll make sure to get to you. But the first question that I have here on my list, and one that came up a lot during the live stream, is how they plan to get samples collected by Perseverance back to Earth. So I'm thinking maybe, Matt, you talked a little bit about the instruments and science objectives.
Right. Well, one of the things that I want to point out is that there is a sense in which getting these samples is a race. We want to be able to get see what happens to things on the surface of Mars, how they change, and so on, and get good samples before humans get there, before anything gets there that could contaminate our results. So we're eager to get these samples as quickly as possible. As far as getting them back, there is a mission planned in 2026 that's supposed to go and scoop them up and return them to the Utah desert in 2031. So
okay, so there's a plan. We're not just collecting them in case maybe one day we're going to be able to get them.
Right. Now the mission plans can always change. I mean, NASA gets its orders from higher up, you know, but right now that is the plan in place. And in a sense, it's also a race internationally, because the Chinese, now that they have successfully put an orbiter around Mars, have expressed that they plan to have a sample return mission in the 2030s. So whatever results we get, honestly, is going to fuel science for years to come. We're still studying the Apollo moon rocks more than half a century later, still writing new papers about them, still making new discoveries about them. And it'll be the same thing with Mars. It's a completely different world, and what we find is going to be completely different from anything we've ever experienced before.
I'm thinking, Ken, this will be a good question for you. Correct me if I'm wrong. But Melinda was asking, what happened, in theory, at least, to the water that used to be on Mars?
Well, there's several possible explanations, or a combination of all three. Number one, it goes into the atmosphere. Some of it dissipates into space. Number two, it goes down into the ground and becomes groundwater or ground, frozen water underground. And number three, it gets frozen at the poles and in the atmospheric clouds. What we're hoping for, especially with the RIMFAX radar, ground penetrating radar, is maybe we find some liquid water underneath, or frozen water underneath that lake bed. Because after all, that lake bed was a sitting pool of water for a long time. Some of it had to seep into the ground, you'd think. So hopefully we find some of that.
You know, and to add to that, Ken, we currently have a mission flying in orbit called MAVEN, and it was sent to Mars to study the atmosphere. And the results have shown that over time, the particles coming off of the sun have stripped a lot of the Martian atmosphere away. And the net result is that if you have liquid water on the surface, it will almost instantly evaporate. So we've learned a lot about the history of how that process has taken place, and frankly is still taking place today on Mars. It's basically due to the fact that Mars does not have a strong magnetic field the way that Earth does. It lost its magnetic field many millions of years ago. But before that point in time, the evidence that we have from all of our landers and orbiters has been that there's a sizable amount of actual of water that was on Mars way back then, before the magnetic field went down and the atmosphere was stripped away. So that's where you see all these river flow areas where it just looks like a delta on Earth, and yet it's just preserved in rock because the water's long gone.
Wiley is wanting to know how you protect the camera lenses and probably the other instruments on Perseverance from sandstorms on Mars. Who wants to take that one? Wave at your camera for me, because I've got my list and I'm like, does that fall under planetary cataclysm, Doug?
Well, I don't know. You know, when the Curiosity rovers actually landed, the Curiosity Spirit and Opportunity, when they landed, their solar panels would become covered with dust. It's actually an instance where there was a dust devil flying around on one of the solar panels, and immediately the rover began picking up energy. So it's really difficult to keep dust and such off of surfaces, off of lenses. This is also one of the reasons why we're actually powering the rover with nuclear power, the last two rovers. So it is an issue. If they get really muddy, I don't think they really have a way of cleaning them off. We're just keeping on the fact that the particles won't stick to the lenses, and so there's not a lot of water there on Mars. So unlike here on Earth, when your camera lens usually gets dirty or an eyepiece, it's because you have condensation on the eyepiece. The eyepiece fogs up. Dust and particles actually are attracted to that. They coalesce on the eyepiece or on the lens. And so you don't really have that issue with Mars, because Mars is incredibly arid. The atmosphere is only 1% of that of Earth. So you really don't have that issue as you would with respect to, say, here on Earth.
Excellent. Let's see. The next question that came in was, will the drones footage, I'm guessing Ingenuity helicopter, will footage from that be streamed to the public? Is that made available somehow in a real-time sense?
I don't think it'll be real time, but I do think the footage will eventually make its way to us. Because the first thing, the footage goes straight back to the rover. And then the rover will communicate or uplink it back to Earth along with all the other data it uplinks when it's uplinking data at several points during the day, as orbiters are passing overhead, or when it has direct line of sight with the Earth to communicate directly.
Yeah, and it's also worth noting that the actual flights are not going to be very long, and they're only planning up to 5 flights. So again, not a lot of power available. So the helicopter is not going to fly all that high and all that far. It's really more the technology demonstration.
Sure, and I believe it was Alan who pointed out that the current uplink speed from the rover right now is on the order of 2 kilobytes per second. That is really, really low bandwidth. You wouldn't even get 144 YouTube video quality out of that. it's downright awful. So better to save it, compile it, and then send it all back as a stream that can then be recompiled back here on Earth and constructed into a video.
Yeah, absolutely. Which, a question like that, it seems like the crux of that is that people really do want to be able to interact with NASA science and NASA robots as much as they can. Like, how many different ways can we incorporate what NASA is doing into what we're doing at home or at school or in clubs and stuff like that? And Sarah, I know that you had done a little bit of work bringing resources together for groups like that.
Mm-hmm. Yeah, so there's lots of different ways you're going to be able to follow this mission on the way. So this rover already has a Twitter account. It's NASA Persevere, not NASA Perseverance. It's NASA Persevere. So you can go tweet. I can go look at it right now. Follow it on Twitter. The homepage for all things Mars is really easy to remember. It's mars.nasa.gov, and that is kind of your homepage for everything that's happening. You can follow like live events on there, see when stuff is going to be happening, when they're going to have briefings, because once the mission gets going, they'll start having like things like briefings where they'll talk about like, oh, we found this, and they'll put a presentation together, and then they'll have someone present it. And so they'll put those kind of events, they'll post like telling you, okay, this coming up will be this event. And on that same place, you can find posters. Actually, all the posters behind me are posters that I printed for free from NASA's website. So have a bit of Mars and NASA in your house.
Oh, nice.
Mm-hmm.
And I think you're right. I think people do crave that sort of personal connection. I think that's exactly why we hope to send humans there one day. Because these robots are incredible, don't get me wrong, but they don't replace the human experience.
That was another question that came up in the chat was, is it true that in 2024, NASA wants to send humans to Mars?
Not Mars, but we are planning to send humans back to the moon in 2024. We haven't been since 1972. So this is really kind of exciting all by itself. The plans are currently, and we're still building the hardware and testing it and so on. So, fingers crossed the schedule doesn't slip. We're hoping to land the first man and woman, well, the first woman on the moon, and the first man since 1972. In 2024, and we want to have a permanent base there established around 2028, around the south pole of the moon, where we found evidence of liquid water. But having a permanent base there is key in trying to understand what's going to be involved in getting people to Mars, to spend a year on Mars, and then months there, a year on the surface, and then months back. So yes, we're not going back to Mars in 2024, but we're starting in deep space exploration again, and that's kind of a necessary step.
Yeah, the Artemis program going back to the moon is going to help us develop and practice the techniques that we will use to live on Mars in the 2030s. So things like how to live off the land, how to farm the moisture out of the soil. Things that we'll really need, because when you go to the moon, you can be home in about 3.5 days if something goes wrong. And the space station, you can be home in about an hour. When you go to Mars, it's a 2-year journey because the planets only line up every 2 years. So you have to take, if we can bring water, which is one of the heaviest things that we bring, if we can find it there, we can have a lot more cargo capacity for food and other things like that. Besides the water, we can get hydrogen and oxygen from that for fuel and oxidizer. We know that on Mars that they're, depending on I've seen statistics that at the poles, about 60% of the Martian regolith, meaning the soil on Mars, is water. Around the equator, it's more like 5%, but there's water everywhere. We just need to learn how to farm it. Think of Luke Skywalker on Tatooine when he was a young man, having to farm the water on a desert planet. That's what we will have to do on Mars. And one of the reasons why we're going back to the moon, it's not just for fun, it's to learn how to live in an inhospitable place for a really long time. Think of the ultimate camping trip.
Yeah, and if you are like a kid out there watching this today, you are the generation that is going to be the one that's going to go be the ones who are the astronauts who go to Mars. Yeah.
Yep. Go work on the moon.
Yeah. What is this poster you've got, Mike?
No, I think this one is just, let's, come and, take the night shift on the moon.
Yeah, there is a whole set of posters. This one says teach on Mars. There's a whole set of Mars like job posters that NASA's put together to kind of inspire like young people to like get involved and think about these. It's not just, science and engineering. If we get set up on Mars, you're going to need stuff like farming and agriculture and things like that aren't just like math and science. There's a lot of different topics.
And there is this also. There's a fellow named Elon Musk. Maybe you've heard of him. Owns a company called.
Name sounds familiar.
I hate to plug them here, but they've got the best shot at getting us to Mars before anybody else does, including NASA. Sorry about that. But it's true. 2026, Elon's target date for putting human beings on Mars. And he's building the rockets and testing them right now, failing them in Texas. But he is testing those rockets, and each one of those failures is a stepping stone to later success. Just like the early days of NASA when we were launching Vanguard rockets that blew up on the launch pad, et cetera. So, Elon's got the best shot of getting us to Mars to answer the Mars part of that question in 2026. So
and that rocket that you spoke of, Elon Musk's SpaceX's Starship, they're testing it right now. It will hold 100 people at once. So we're talking about it'll hold over 100 tons of cargo and all that, but it's designed to colonize Mars. It's not sending one or two people, it's sending, part of a town. Very exciting times.
So a question that's come in a little bit recently then, do you think that once we send the technology to change carbon dioxide to oxygen, water, and fuel, will Mars form some sort of atmosphere?
Where's Tony?
I'd like to talk about that just for a second, if you don't mind, because I think one of the real issues we have with Mars, and you already brought it out, is that there's actually no the magnetic field is incredibly weak. So really the key to actually getting an atmosphere on Mars is to first find out how to kickstart the magnetic field. On Earth, we have something that keeps our magnetic field running, and that's the moon. The moon is roughly about 1/6 the mass of Earth. And as it orbits around the Earth, tidal action that it exerts on the core keeps our magnetic field running. We're going to have to find some interesting way to kickstart that magnetic field. So no matter what we do, if we become good about, say, guiding a comet, an asteroid, or some other object into a comet into, say, the Mars to generate water, and if you do that, you've got to find some way to keep that atmosphere there, and you can't do it without a magnetic field. So that is one of the real terraforming obstacles that we need to overcome. I don't think it's insurmountable. I do think it's a challenge for us. And this has been a great question, because this is probably the next thing that we need to begin studying, is how do we actually kickstart a magnetic field of a planet? Because we also have another planet that's very much like Earth, and that's Venus. We need to figure out how to reverse its rotation and kickstart its magnetic field as well. So there's a lot of challenges out there for us. And that's why we need young people and people actually examining these large problems of physics and planetary terraformation. We can do it, but it's just something that we're going to have to start doing.
There is the ethical question: do we touch Mars? Do we?
That's a good one.
I mean, there's a fair question. If we find out that there are living Martians there currently, do we have the authority to go in there and change Mars because we want it to be different? That's a good ethical question.
One of the questions that came in was, are there aliens on Mars? And I think if you're an alien on Mars, that means you're one of us.
Yeah.
Right.
Right.
Well, we have robotic aliens on Mars. Now, but whether there is life on Mars, that's the other question.
Is there life on Mars? And that's what Perseverance is supposed to help us figure out, right?
Right. We don't expect little green men, but it's perfectly possible that there's microbes where we haven't quite looked yet.
Yeah,
and that's what makes Jezero Crater so interesting.
I brought it up during one of my talks. We've explored so little of the surface of Mars up close so far. We've only been at it for 50-something years. And, there's way more to discover. And as Matt pointed out, there's a whole lot of places we just haven't looked yet.
Yeah. And if you think about even here on Earth, I mean, we're still discovering, new species of animals, here. So
Sure.
Yeah.
There's a whole branch of study where they look at what they call extremophiles. And these are critters that like to live in places we normally thought life could not exist. At the vents of volcanoes or in deeply acidic waters or in other places like that. And given that we don't have a complete beginning to end picture of how life formed on this planet. We have several hypotheses, but none of them can be considered, theoretically confirmed. It's entirely possible that there's some what we would call an extremophile living in some place of Mars we just haven't thought to look yet.
Well, the most likely place to find life on Mars, if it's there now, is probably going to be the most difficult place to study. There's these canyons that dwarf the Grand Canyon. And down in these canyons, you're going to have some protection from the solar and cosmic radiation. You might have liquid water oozing out of the ground. But those are the hardest landing sites to go to. There's no solar. I mean, solar power would be difficult, and the rocks to bang into on your way down. And we're landing in fairly easy places, relatively easy now, where like Jezero crater, it's exposed to a seriously bad solar and cosmic radiation situation that's not mitigated by an ozone layer, an atmosphere, the magnetic field you guys have talked about. It's harsh and dry and temperature extremes. And down in these canyons are a little bit nicer, but they're harder to get to.
And I think part of this question really is two questions. It's, was there ever life on Mars? And the corollary, is there life now on Mars? If you go back again some 3.8 billion years, Mars and Earth had very similar environments from what we can tell. It would be reasonable to think, in fact, some hypotheses suggest there may have been life on Mars before Earth. That life would probably be very simple, microbial type of life. And this is one of the reasons that Perseverance is going with the scientific packages it has, to look for evidence of past life and potentially current life in some of those difficult places you mentioned, Alan.
Because Mars definitely cooled a lot faster than Earth did. It's smaller and further from the sun. So in terms of habitability, Mars was habitable quicker or sooner after the solar system was formed than Earth was. So there's a lot of merit to that theory. Sorry, Ken, go ahead.
No, I was just going to say that the places we're exploring on Mars, we can't explore on Earth anymore. They're gone. A 4 billion year old lake bed, good luck finding one of those on Earth, because obviously something low to the ground like that is going to get filled in by other sediments and everything else and covered by hundreds of feet of rock. So that's going to be gone. So we're really looking back in a window of Earth's past history. So whenever we send a spacecraft out to explore another planet, there's a rear view mirror you can imagine on that spacecraft looking back at home, because it's going to tell us more about the early formation of the Earth as well.
Sure, absolutely.
Oops, sorry.
Oh, all right. I just mean to say that whether we find evidence that past life existed on Mars or whether we don't, I think both of those would be very, very interesting answers, because we don't know how likely it is that life forms given the proper circumstances, right? We only have the one data point. So if it turns out that we get to Mars and we find out, yeah, the conditions were right, but life didn't form, that opens up a whole lot more questions about why life formed here. A whole lot more things for us to explore here and there. So, yes, finding life or even the evidence of past life on Mars would be exciting, but it would also be interesting if we didn't, I think.
And Matt, if we did find that evidence of past life, now if we can say, geez, here in one solar system, in one tiny little corner of the universe, we've got two instances of life coming about, then you start to ask the question of the thousands of exoplanets we've discovered. It really would beg the question, the likelihood of finding life out there, maybe even intelligent life, goes up rather dramatically, right?
Absolutely, yes. Very good.
Back to Ken's point that he made earlier about it's a window looking at Mars's past as a window into looking at Earth's past. We know that Mars was covered in oceans and flowing rivers, potentially oxygen because of all the rust that's on, iron oxide that's on the surface. Something happened, something pretty drastic happened to Mars if it had life, to kill the life, or I'm assuming that it's not there. It may very well be there, but we can also maybe learn how to prevent that from happening here. It was once a great candidate for life. Now it's a frozen desert. is that something we can prevent here on Earth? So I think there's a lot. What Ken said is exactly right. We could learn a lot about here, and ultimately that's why we're going there from Mars. So
yeah, I think that's a super point. I really do, and I definitely agree with both you guys on the window into what's happening with Earth. One of the things that we've learned from Venus is that at one time Venus may have been very much like Earth as well, and for some reason something happened, something caused its greenhouse effect to tip over into generating acid rain, sulfuric acid rain. By looking at Venus, we've been able to understand and look at those same processes happening here. And to some extent, we see the exact same progression that's beginning to happen in our own atmosphere now with the effects of global warming. Is there something, just like Mark alluded to, something that happened that caused Mars to lose its atmosphere? What if it was an impactor that actually hit Mars and actually shattered or blew much of its atmosphere away? We certainly see a lot of near-Earth asteroids right now that we're not dealing with. So those are some things I definitely agree with Mark and Ken as being a window into the past, and also a portent for us to take note of, to develop those technologies to preserve what we have here as we begin to expand out into our own solar system.
Great stuff. Great stuff. I want to bring it back to what happened today. And in particular, just those last minutes, the 7 minutes of terror of entry, descent, landing, and then the confirmation that that Perseverance was on the ground and safe. And our digital media staffer is actually going to sort of replay the animation that we had prepared for that. So I know we here on this call, we won't be able to see it, but Brent, roll the tape. And Mark, maybe I had you down as our EDL expert on the list, but maybe if you could just, I know you can't see what's going on, but sort of talk us through what that was like, and then others can jump in with the discussion.
Sure. Well, as we talked about in our presentation, let me come back. I wanted to make a point during the presentation that we didn't have time to make. When you launch into space, you have to go 17,500 miles an hour, more or less, to get into orbit. And then to get to escape velocity, you multiply whatever the orbital speed is by the square root of 2. So you multiply it by 1.414, so 41% more. So it leaves the Earth roughly about 25,000 miles an hour. As it's traveling, it has not escaped the Earth's gravity well, and the Earth is slowing it down. So it's slowing down most of the way to Mars, and then there'll be a point where the Mars gravitational pull and the Earth equals out, and then it will start going downhill and start gaining speed again. And it's between 12 and 13,000 miles an hour when it hits the atmosphere, and that's where all the fun begins. It had a reentry shield on the bottom that's called a hypergolic shield. Ablative shield. And what happens is they just want to manage that heat for a few minutes while it goes through the critical point up to 4,000 degrees. So what happens is a lot of times it's a phenolic resin that when it heats up, it starts to burn and flakes away. That takes all that energy with it. So they're dissipating the energy as well as protecting and that's serving to slow the whole system down. Then it slows down to about 900 miles an hour, and one of the largest parachutes ever made, a supersonic parachute, opens up. That slows it down to about 200, where it is dropped, and the descent stage takes over, and it flies it like a platform. And as Ken so adroitly described, there's software in there that starts to look at the terrain, comparing it to another map that it has, looking for a particularly good place to land. And you saw when that was happening, that happened, within several seconds. So all these things had to happen. There were thousands of things that had to happen right for it to land at 2 miles an hour. And there's a whole lot of things that could have gone wrong. And the fact that we're 0 for 2 right now, after Mars has such a history of failures, right? For about 40% of the missions survive. I think that's a testament to engineering, the power of mathematics and science. It is really seeing it happen in real time. There's nothing like that. I don't know about y'all, but I'm still on an adrenaline high here.
Mark, it's interesting when you say that, because I always think of Mars just being so hard, and yet we make it look so easy.
Yeah.
When you think about the realities of Mars being actually very different from Earth when it comes to the engineering of a landing, right? Yes. If it had no atmosphere like the moon, we know retro rockets do a pretty good job and we have a pretty controlled descent. But now we're dealing with an atmosphere that's enough to destroy your spacecraft 10 times over. And it doesn't take much. If your attitude is off by just a degree or two, a heat shield isn't going to be effective. So we're literally guiding this projectile, in a guided format through the atmosphere to keep it at just the right angle to let that heat shield do its work. But it's not enough of an atmosphere to really slow you down. So that's why you need the world's most sophisticated supersonic parachute that only weighed 100 pounds. And if that's not hard enough, we can only get you slow enough where now we've got to drop you on a sky crane, because any other technique that we're aware of, like retro rockets for a craft that weighs a ton, literally, those rockets would need enough fuel that would be so heavy the whole thing doesn't work. We couldn't even get it off the Earth. And on and on and on. I mean, it looks so easy. And by gosh, it looks great when it works. But like you said, there are a million reasons why it wouldn't. And it did today. And that's what makes today so special.
Yes. So when we send people there, the capsule is going to be a lot larger, a lot heavier. We're going to have to figure out another way to land. And I know that the engineers are working on that. But it's going to be pretty rough.
Well, when you say rough, I mean, I think of at parachute deploy, you're talking 9 Gs, right?
Yeah,
I mean,
right.
You're not going to be subjecting astronauts to 9 Gs, so we need a new mechanism there.
Well, and that's also after they've been in space in microgravity for 7 to 9 months. So their bone density is way down. They're going to be in for a very, very rough landing. And then if something happens, you can't go home right away. So it's an interesting setup. And then the other problem with people is we don't know how we're going to react psychologically to not being able to see the Earth. It'll just look like a star in the sky. And we have a lot of analogs in Antarctic bases and things like that, but those are typically 6 months at a time. We don't have the asynchronous communication that you would have with people on Mars because of the distances involved. So it's something that we're working on very diligently. So by the time the children that are in school now are in college and graduated, they'll be able to go to Mars and we'll have systems in place and it'll be a piece of cake.
So the message to them is start now, right? Start now.
Start now. Yeah.
Get ready. It's going to be a wild ride.
I'm encouraged that, yes, even though Mars has a poor safety record, if you want to call it that, in terms of the difficulty of getting things there, I think that even though the numbers are small, if you look over time, we've gotten better and better and more and more successful at sending these things to Mars. So we are learning. And that's the important thing when we consider sending people to Mars.
Yep.
I was going to comment on the psychological aspect. I think from social distancing over the last year, I'm prepared to go somewhere else.
Yeah.
So I'm going to grab some more questions out of the chat here just for our final few minutes. And the last couple of ones here have to do with Perseverance specifically and how it was constructed. Some folks seem to have noticed that they see dots and dashes on the wheels, and they want to know if Perseverance is leaving Morse code in the Martian soil.
That was the last one, Curiosity. Yeah, that we were, JPL was told the original wheels had JPL on them in the tread, and NASA told JPL, no, you can't stamp can't stamp your name all over Mars. So they made some with the dashes and dots, And those were actually Morse code for JPL. So there. So NASA finally got smart and said, no, you can't have any kind of holes or any kind of cryptic things on the wheel. So the wheels are real plain on Perseverance with just straight across grooves that in no way spell JPL. So yeah, he's the person that asked that question was referring to the dashes and holes in the previous one.
Curiosity.
These wheels. Yeah.
And how long did it take to construct Perseverance? Does anybody know? I imagine a while.
Yeah, years, several.
And it goes without saying that it's obviously the platform is based on curiosity. So, we're able to take a lot of that same design and bring that forward to this rover.
Yeah, and I know for a while before it was even named Perseverance, because Perseverance is a really new name for it. It was just the Mars 2020 project, because obviously, like someone was saying previously, there's only a certain time every so often we can try for a mission, because you have to have everything lined up properly. And so they kind of know in advance when the next ones are going to be. And so they're like, we should have one this year because you're in the right cycle for it.
Well, everybody, what do you think? The next time NASA lands a robot or a human on Mars, should we get back together and do it all over again?
Oh, absolutely.
Absolutely.
Yeah.
Always happy to bring the band back together.
I agree. Listen, we've been at this for several hours now, but every minute of it has been a thrill. There were some moments of it that were nerve-wracking. They were so thrilling. But I want to thank each of you for bringing your knowledge, your experience, and your time to this project to share with the museum audiences, to put on today's program, to put the research into all of your presentations, to getting people connected to science. Of course, that's what we love to do at the Museum of Natural Sciences. And each one of you just did a fantastic job today. So everybody who's watching the video, you can drop applause emojis into the chat for all of our fabulous solar system ambassadors. And you all have my thanks and respect for all of your help today.
Thank you, Chris.
Our pleasure.
Thank you.
Real pleasure. Enjoyed being with you guys.
It was awesome.
And Alan, you can co-host programs with me out of the museum anytime you like. Come back anytime.
I will. I enjoyed you being a co-host with me. And I also want to throw out kudos to the people of this area, of this part of North Carolina. When the Nature Research Center opened, for people who don't know what that is, that's the new part of the Science Museum. There was a 24-hour, there was a 24-hour opening event that we were there, NASA-JPL, and had some friends from Pasadena. JPL came out and we set up a little demonstration table. And at 4 o'clock in the morning, I walked out with a friend from JPL, and there was a line of people just going blocks waiting to get in. And he said, "This is Raleigh, North Carolina, isn't it?" And I went, "Yeah, you're where you think you are, where it said on your plane ticket." And he said, "There are very few places in this country that would pull something off like this with this many people." He said, "I don't think we could do this in LA. But look at all these people just waiting to get in at 4 o'clock in the morning." And then when Curiosity landed, the museum gave us the auditorium to do what we're doing now in. It was packed in the middle of the night. I can't say enough good things about both the Natural Sciences Museum and the people of this area that just come out in droves to whatever we do.
You're here.
Absolutely.
Thank you, guys. This really is rocket science.
Absolutely. I want to extend a special thanks and appreciation to the educational events team at the Museum of Natural Sciences, Carrie, Miranda, and Hugo, who I know put much effort into making today's program go off with as few hitches. I don't think anything went wrong today. And that was because of their help. And I want to thank the digital media technician who is on the back end of making sure that everything worked. from the audio and the video to bringing in the NASA feed. Brent McCraven on the other side of the wires here did a phenomenal job as our producer. Big round of applause for all of those people. Hey, everybody. That's it. I'm going to wrap up things here. Thank you for being with us. Thanks for joining us on today's exploration of Mars. How much this was just the best thing ever. This was the most fun way to spend a Thursday that I could imagine. But you know what? The Museum of Natural Sciences here in Raleigh, North Carolina is bringing you great, exciting programming all the time. So make sure that you visit naturalsciences.org, the museum's website, to see more fun, interesting, cool events that are coming up in the near future. And follow the museum on social media. We're on Facebook, Twitter, and Instagram as @naturalsciences. And of course, a lot of the live streaming that we do, live programs that we're bringing you, happen right here at the museum's YouTube channel and at our Facebook page. So if you're on YouTube with us right now, you can click subscribe below, ring the bell next to that to get notified when we're bringing live stream content to you or upload new great science videos. There's lots of ways to be connected with what's happening here at NCMNS any day of the week at any time. So thanks to all of the NASA-JPL Solar System ambassadors for being here. Congratulations on another successful landing on Mars. To all of you and to the NASA team. And thanks everybody for tuning in with us. We'll see you next time. Bye, everybody.
Bye, all.